when Jupiter went to kill Earth. The shocking truth about the giants of the solar system, the secret they've hidden from you your whole life. I'm about to tell you a story that will turn everything you thought you knew about your place in the universe upside down. A story about how you miraculously survived. How your ancestors, and their ancestors, and every generation of humans before you existed on the razor's edge of complete annihilation. And the most terrifying part? Most of you don't even suspect it. Because out there, in space, 778 million kilometers away, hangs an object that could erase all human civilization from the face of the universe with a single movement. And not even before it appeared, but before humanity itself emerged. And this object isn't a black hole, not an exploding star, not a killer asteroid. It's a planet. A planet you've seen in school textbooks. A planet you may have observed through a telescope. A planet with the beautiful name Jupiter. But the truth about Jupiter, and about its giant brethren, is so terrifying, so incredible, that scientists still argue whether it should be shared with the general public. Because when you understand the true scale of these monsters, when you realize what they did to our solar system billions of years ago, you'll never look at the night sky the same way again. Ready for the truth? Then buckle up. This will be the most terrifying journey of your life. Part 1. The great lie of school textbooks. How they deceived us from childhood. Since childhood, from the moment you first opened a natural science textbook in first grade, you were systematically, methodically lied to. This isn't a conspiracy theory. It's a documented fact that astronomers themselves admit. Remember those colorful pictures? The solar system drawn as neat little circles on a white background. Planets arranged in a straight row, like colorful beads on a string. Mercury, a tiny gray ball. Venus slightly larger. Earth, the blue beauty with white clouds. Mars, reddish. And somewhere further off to the side hangs Jupiter, a yellow-orange sphere that looks maybe 3 times bigger than Earth. 5 at most? Next to it, Saturn modestly shows off its rings, looking like a Christmas ornament. Uranus and Neptune are somewhere far away, blue, quiet, unnoticed. Looks cute, doesn't it? Safe. Understandable. As if someone carefully arranged the balls on a shelf, from smallest to largest. That is the most dangerous lie you've ever been told. Because this picture does something terrible to your brain. It kills the most important sense you need to understand space. It completely destroys your sense of scale. And scale, that's what defines life and death in the universe. Scale decides who survives and who gets torn apart by gravity. Scale determines whether a planet can hold an atmosphere or whether it gets stripped away by solar wind. Scale decides whether a world becomes a home for life or remains a dead rock. And school textbooks killed that feeling in you before it could even form. You might ask, why? Why did educated people, astronomers, scientists let this happen? Why didn't they insist on the correct proportions? The answer is simple and sad. Because the truth can't be drawn on a piece of paper. Think for yourself. If you tried to depict the solar system to scale, you need a sheet of paper the size of a football field. No, wait, 10 football fields. And even then Earth would be a dot smaller than a pinhead, impossible to see without a magnifying glass. And Jupiter? Jupiter would be an orange. A big, ripe, juicy orange that you hold in your hand. Picture this. You're standing on the edge of a giant football field. In the very center lies a huge beach ball, more than 1 meter in diameter. That's the sun. A few meters away, a tiny dot barely visible. That's Mercury. A bit farther, another dot slightly larger. Venus. Even farther, Earth, a dot the size of a poppy seed. Now walk. Walk across this field. 10 meters. 20. 30. 50. 70. And here, at a distance of almost 80 meters from the central ball, you find An orange. That's Jupiter. Now do you understand why everything in textbooks is drawn incorrectly? Because an accurate drawing wouldn't fit on any page. Because if you showed the real scale, children simply wouldn't understand that it's all one system. They'd think these were different things on different pages. But here's the problem. By choosing convenience over truth, the creators of textbooks deprived entire generations of people of the ability to understand how terrifyingly huge gas giants truly are. And how insignificant we, Earth-dwellers, are compared to them. Try right now, this very moment, to erase all those toy pictures from your mind. Forget the neat rows of planets. Wipe the school posters from your memory. Instead, imagine yourself as a passenger on a real spacecraft. A genuine, large ship, the size of a multi-story building. You're flying toward Jupiter. Not past it, not into orbit around it. You're flying straight at it, getting closer with each passing second. At first it looks like a bright star. Then a small disk. You're still far away, and nothing special is happening yet. Yeah, a planet. A big planet. So what? But you keep approaching. And the disk grows. Slowly. Relentlessly. It becomes the size of a coin you hold at arm's length. Then the size of a plate. Then a car wheel. And right here, something in your brain starts screaming that something is wrong. Because it keeps growing. It begins to fill the window. It becomes bigger than the window. It starts to fill everything you can see. And suddenly you realize, with primal, animal terror, that this isn't a planet in the usual sense. It's a wall. An endless wall of gas rising into the heavens, with no end to the right, left, above, or below. You look right. The wall of gas disappears beyond the horizon. Look left, the same thing. Up, nothing but bands of clouds fading into infinity. Down, the same. The stars have disappeared. The sun has disappeared. All of space has disappeared. Only this monstrous wall remains, filling your entire vision, your entire perception, your entire existence. And you, a tiny grain of sand before it. Your ship, a speck of dust. All of Earth, if you brought it here, would be a speck of dust. This is the real Jupiter. Not the cute orange ball from textbooks. But an absolute, incomprehensible, mind-blowing colossus before which everything human seems not just small, but non-existent. Now let's do some mental math. Not because it's interesting, though it is, but because without concrete numbers, your brain will simply refuse to believe what I'm telling you. Take our planet Earth. This entire huge world. A world with 7 continents and 5 oceans. A world where you can fly on a plane for 10 hours straight across the Pacific Ocean and still only see water. A world where 8 billion people live, millions of animal species, trillions of trees. A world that seems infinite to us. Now imagine we take this Earth and start stacking copies of it inside Jupiter, like tennis balls in a giant sports hall. How many Earths could fit inside? Before I tell you the answer, try to guess. Don't read further. Just think and name a number. 100? 200? Maybe 500? Ready for the answer? 1,321 Earths. Read that number again. Slowly. Out loud. 1,321. This means you can take our planet, make a copy, then another, and another, 1,321 times, and all of them would disappear inside Jupiter, like drops in an ocean. 1,300 worlds. 1,300 complete sets of oceans, continents, mountain ranges, atmosphere, everything. All this unimaginable mass of matter would simply dissolve into Jupiter's volume without a trace. Think about it from another angle. Imagine every person on Earth got their own personal planet. 8 billion people, 8 billion copies of Earth. Each has their own. And even then we'd only fill a tiny fraction of Jupiter's volume. We need hundreds more planets. And here's where the real horror begins, because volume is only half the trouble. The true terror lies in the mass. You see, when we say 1,321 Earths can fit inside Jupiter, we're talking about empty space. About how many Earth-sized balls you could cram into Jupiter's volume if you removed all its contents. But Jupiter isn't empty. Oh no. It's packed with matter so densely that its mass is 318 times Earth's. Wait, you'll say. 318 is much less than 1,321. What's wrong? Here's what's wrong. This means Jupiter is much less dense than Earth. Our planet is rock and metal, compressed by gravity into a solid ball. Jupiter is mostly gas, hydrogen and helium, the same substances the Sun is made of. But even being gaseous, even being less dense than Earth, Jupiter weighs 318 times more than our world. Imagine an experiment. You take giant space scales. On one side you place Jupiter. On the other you start stacking everything else. Saturn, the second largest planet in the system. Uranus, the ice giant. Neptune, its twin brother. Mars, the red planet. Venus, Earth's twin. Mercury, the tiny world scorched by the sun. And Earth itself, our home. 7 planets. Everything that exists in the solar system besides Jupiter. And what happens? Jupiter still outweighs them. And then some. By 2.5 times. This isn't a planet. It's an absolute dominant. A gravitational monster beside which everything else in the system is just space junk. And this monstrous mass does to Jupiter things that defy comprehension. You've heard that planets revolve around the Sun? Forget it. That's a simplification that works for small planets like Earth, but it's completely wrong for Jupiter. Because Jupiter is so massive that it pulls the Sun. Yes, you heard right. Jupiter, a planet, makes a star, the Sun, move. How is this possible? The thing is, when two objects orbit each other under gravity, they don't actually orbit each other, but around a common center of mass called the barycenter. For most planets in the solar system, this barycenter lies deep inside the Sun, practically at its center. So it looks like planets circle a stationary star. But Jupiter is a different story. It's so heavy that the barycenter of the Sun-Jupiter system is not inside the Sun. It's located above the star's surface, in open space, about 47,000 kilometers from the Sun's photosphere. This means that technically, Jupiter doesn't orbit the Sun. Both, the planet and the star, dance in a deadly gravitational waltz around an invisible point in empty space between them. If you could observe the solar system from the side, from a huge distance, you notice that the Sun slightly wobbles, describing tiny circles in space. That's Jupiter pulling it now one way, now another, like a huge dog pulling on a leash. And this is the only object in the entire solar system that has such audacity and power. Even Saturn, the second largest giant, isn't massive enough to pull the barycenter beyond the Sun's surface when it's on the opposite side from Jupiter. Jupiter is king. An absolute, undeniable, ruthless king of gravity in our cosmic home. And now imagine that this machine, nearly 143,000 kilometers in diameter, for comparison. Earth's diameter is only 12,742 kilometers, doesn't just hang motionless in space. It rotates. And it rotates at such a crazy, incredible, mind-blowing speed that it seems like a violation of the laws of physics. A day on Jupiter lasts less than 10 Earth hours. Just 9 hours, 55 minutes, and 30 seconds. Stop and think about that. An object larger than 1,000 Earths makes a full rotation faster than you can get a normal night's sleep. Faster than a standard workday lasts. For perspective, Earth's equatorial rotation speed is about 1,670 kilometers per hour. Not bad, right? You're hurtling through space at that speed right now, just sitting still. Jupiter's equatorial rotation speed is 45,000 kilometers per hour. 45,000 kilometers per hour. That's 27 times faster than Earth's rotation. That's almost 37 times faster than the speed of sound. That's faster than the fastest rockets ever built by humanity. And this speed creates consequences that change the very shape of the planet. Because of this insane rotation, Jupiter literally flattens itself. Centrifugal force is so great that the planet stops being a sphere. It becomes flattened at the poles and bulged at the equator, like a balloon being spun too fast. Jupiter's equatorial diameter is 143,000 kilometers. Its polar diameter is only 134,000. A difference of 9,000 kilometers. For comparison, that's more than Earth's entire diameter. And what does this mean practically? If Jupiter had a solid surface, it doesn't. But let's imagine, and if you could stand on it, you couldn't. But let's imagine, then scales at the equator would show significantly less weight than at the poles. Why? Because the planet is trying to throw you off, like a wet dog shaking off water. Centrifugal force at the equator is so strong that it partially counteracts gravity. Imagine a planet weighing 318 times more than Earth, with gravity 2.5 times stronger than ours, spinning so fast that it tries to tear off anything on its surface. This is the real Jupiter. Not a quiet orange ball from a textbook, but a boiling, spinning, self-transforming monster that lives by its own insane rules. Like and subscribe to our channel so you don't miss our new videos, which, as always, push the boundaries of the known. And we continue to push the boundaries of the unknown. Atmospheric hell, storms that devour worlds. Now let's talk about Jupiter's most famous feature, that thing that appears in every documentary, about the Great Red Spot. But first, forget everything you thought about it. Because when people hear the word spot, they imagine something like a mole, a small mark, a cosmetic defect. The Great Red Spot is not a spot. It's a hurricane larger than planet Earth that's been raging non-stop for at least 350 years. Yes, you understood correctly. 350 years. Continuously. Without pause. When Italian astronomer Giovanni Cassini first spotted this formation in 1665, Peter I hadn't been born yet. Tsar Alexei Mikhailovich ruled in Russia, and Europe was ravaged by plague. Since then, dozens of human generations have passed, world wars have happened, humanity invented electricity, cars, computers, went into space, and this spot is still there, still spinning, still devouring clouds and gas in its eternal vortex. And the scariest part, we don't know how old it really is. Could be thousands? Tens of thousands? Hundreds of thousands? Imagine a hurricane on Earth. The most powerful, most destructive cyclone you can imagine. Say, Hurricane Katrina, which destroyed New Orleans in 2005. The diameter of its eye was about 40 kilometers. Wind speed, 280 kilometers per hour. A planetary scale catastrophe. Now take that formation and enlarge it 300 times. The Great Red Spot's diameter at the time of writing this text is about 16,000 kilometers. Though, to be fair, the spot is slowly shrinking. When it was first accurately measured in the late 19th century, its diameter was about 40,000 kilometers, 3 times Earth's diameter. Now it's only 1.5 times larger than our planet. But even in its reduced state, this monster remains the largest storm in the solar system. You could take our entire planet, with all its oceans, continents, cities, forests, deserts, and throw it into this storm, and it would fit freely without touching the edges. Moreover, the moon could fit alongside it. And the winds. Oh, the winds, they are a separate song of horror. At the edges of the Great Red Spot, winds blow at speeds of 500 to 600 kilometers per hour. For comparison, this is faster than the strongest tornadoes on Earth. Wind speeds in EF5 tornadoes, the most destructive category, reach 480 kilometers per hour. And these aren't brief gusts that last seconds. This is a constant, continuous flow that's been blowing at such speed for years, decades, centuries. What happens inside? We don't know for certain because no probe has ever flown into it, and probably never will. It would simply be torn to pieces. But from infrared observations, we know that the temperature is higher at the center than in the surrounding atmosphere. This is an anticyclone, a high-pressure zone where gas rotates counterclockwise in Jupiter's southern hemisphere, rising from the depths and cooling at the top. Clouds that fall into this vortex are ground up by turbulence, chemically altered by solar radiation and high temperatures, colored this characteristic reddish-brown hue, likely due to complex organic compounds or phosphorus compounds formed under extreme conditions. And all of this spins. One full rotation around the center takes about 6 Earth days. Imagine. A cloud of gas the size of a planet completes a full circle in a week. These are speeds at which any material on Earth would simply turn to plasma from friction. The Great Red Spot isn't alone. It has younger brothers and sisters, an entire family of storms that are born, live, and die in Jupiter's atmosphere. In 2000, astronomers observed an incredible event. 3 white oval storms that had existed separately since the 1930s suddenly merged together, forming a single large vortex. By 2006, this vortex changed color from white to red and was dubbed the Little Red Spot or Red Spot Jr. The diameter of this newborn monster was only about 8,000 kilometers, roughly the size of Earth. Yes, this doesn't surprise you anymore, right? Only the size of a planet. In 2008, something even more dramatic happened. The Little Red Spot approached the Great Red Spot. Astronomers around the world held their breath. Would the 2 giant hurricanes collide? Would they merge into a superstorm? Destroy each other? The reality turned out to be more brutal and straightforward. The Great Red Spot simply absorbed its younger brother. Like a giant whirlpool swallowing a smaller one. The Little Red Spot disappeared, torn apart, and consumed by its elder sibling. It was like watching one world devour another in real time. But the family doesn't end there. Scattered across Jupiter are dozens, if not hundreds, of smaller storms, white ovals, brown barges, elongated vortices, cyclones, and anticyclones of all sizes. Some exist for years, others appear and disappear within months. Jupiter's atmosphere is a constant battlefield where continent-sized storms wage war against each other for energy and space. Now look at those famous bands that make Jupiter so recognizable. Light zones and dark belts encircling the planet parallel to the equator. At first glance, they look peaceful and beautiful, like stripes on a tiger. But in reality, these are boundaries between giant jet streams, rivers of wind that race in opposite directions at speeds up to 600 kilometers per hour. Light zones are areas of rising gas where ammonia is carried up from the depths, cools, and forms bright white clouds at high altitudes. Temperatures that are relatively cold, for Jupiter, around -130 degrees Celsius. Dark belts are areas of descending gas where clouds lie deeper, and we see darker atmospheric layers. Temperatures there are higher, so these regions emit more infrared heat. And here's what's important. There's a colossal difference in wind speed between these zones and belts. Imagine standing at a boundary. On one side of you, the wind blows east at 500 kilometers per hour. On the other side, west at the same speed. The relative difference in speed, 1,000 kilometers per hour. 1,000 kilometers per hour. That's 3 times faster than the speed of sound in Earth's atmosphere. And what happens when 2 streams with such monstrous speed differences meet? That's right, vortices form. Enormous, rotating structures that appear as white or colored spots on the boundaries of zones and belts. Jupiter's entire atmosphere is a giant turbulent machine where energy constantly flows from one form to another. From wind speed to vortices, from vortices to heat, from heat back to motion. And now imagine flying over Jupiter's dark side at night. Solar light doesn't reach this half of the planet. Below you, a chasm plunged into darkness. And suddenly, a flash. Bright, blinding, like an atomic bomb explosion. It illuminates clouds for hundreds, thousands of kilometers around. Then another. And another. And another. Lightning. But this isn't Earth lightning, tiny sparks a few kilometers long. These are discharges thousands of kilometers long, carrying energy thousands of times greater than Earth's most powerful storms. When the Voyager probes first recorded these flashes in 1979, scientists initially didn't believe it. It seemed impossible that lightning could be so powerful. But subsequent observations, by Galileo, Cassini, Juno, confirmed. Yes, storms rage on Jupiter, compared to which even the strongest Earth storm looks like a static spark from a wool sweater. Where does the energy for such discharges come from? From the same convection that powers the entire atmosphere. Hot gas rises from the depths, cools at the top, ice crystals, ammonia, water, collide with each other, accumulating static electricity until it reaches a critical point and releases, bam, as giant lightning bolts that slice through the clouds. And this lightning happens constantly. At any moment, dozens of storms rage across Jupiter. The planet literally flickers with discharges. If you could stand on a platform inside this atmosphere, which, of course, is impossible, you'd constantly hear thunderclaps, a continuous, deafening roar that never stops. Another spectacle that makes Earth analogs pale in comparison: Jupiter's auroras. On Earth, the northern and southern aurora occurs when charged particles from the Sun enter the planet's magnetic field, are directed toward the poles, and collide with the atmosphere, causing it to glow green, red, or violet. On Jupiter, the same thing happens, but the scale. Well, you're used to that word by now. The scale is absolutely different. Jupiter's magnetic field is 20,000 times stronger than Earth's. That's the most powerful planetary magnetic field in the solar system. The magnetosphere, the region of space controlled by this field, stretches for millions of kilometers and reaches Saturn's orbit. And when solar wind crashes into this invisible wall, incredible energy processes occur. Particles are captured, accelerated to relativistic speeds, close to light speed, and directed along magnetic field lines toward Jupiter's poles. There they smash into the upper layers of the atmosphere with such force that the atmosphere begins to glow. But not dimly, like on Earth. They glow with an intensity visible even in ultraviolet and X-ray ranges. The energy released by Jupiter's auroras is equivalent to several nuclear bomb explosions per second. And this continues constantly, billions of years in a row. And here's what's especially interesting. Part of this aurora is caused not by solar wind, but by Jupiter's moons. Io, the innermost of the large moons, ejects tons of volcanic material into space every second. This material ionizes, gets captured by the magnetic field, and forms a giant plasma torus, a donut, around the planet. When this plasma crashes into the atmosphere at the poles, it creates bright spots, footprints of each of the Galilean moons in the auroras. You can literally see the imprints of moons on the planet's atmosphere. But the most dangerous thing about Jupiter is invisible to the human eye. Its radiation. Remember that powerful magnetic field we just talked about? It doesn't just create beautiful auroras. It also creates lethal radiation belts, toroidal, donut-shaped, zones filled with high-energy charged particles. Earth also has radiation belts, discovered by scientist James Van Allen in 1958. They're dangerous for satellites and astronauts, but generally manageable. Jupiter's radiation belts are a completely different level of threat. The radiation level there is 1,000 times higher than in Earth's Van Allen belts. Millions of times higher than a lethal dose for humans. If you found yourself inside these belts without protection, you'd receive a lethal dose of radiation in less than a second. Literally. Your cells would begin to break apart instantly. DNA would tear to pieces. Within minutes, you'd be dead. Even inside a spacecraft with normal shielding, you wouldn't last long. Radiation would penetrate the aluminum hull like bullets through paper. That's why the first probes sent to Jupiter, Pioneer 10 and Pioneer 11 in the early 1970s, were designed with special reinforced electronics protection. Engineers knew radiation would be a problem, but they underestimated the scale. Pioneer 10 received such a radiation dose during its Jupiter flyby that some of its instruments began to malfunction. Communication became intermittent. The probe almost died. After that, all subsequent missions were designed with even more serious protection. Galileo, which orbited Jupiter for 8 years, from 1995 to 2003, was literally armored in radiation shields. And even that helped only partially. By the end of the mission, many of the probe's systems were failing due to accumulated radiation. And now Juno is working there, the most protected spacecraft in history. Its most sensitive electronics are hidden in a titanium vault nearly a centimeter thick. And even so, the mission is designed for only a few years because radiation gradually kills the probe despite all the protection. For humans, a journey to Jupiter is practically impossible in the foreseeable future. Not because of distance. Not because of travel time. But because of radiation. You'd need a ship with meter-thick walls of lead or water to get any protection. And even then, long-term stay would be deadly. Jupiter is protected better than any fortress. It's surrounded by an invisible barrier of killer particles that incinerate anything that dares approach. You might ask, why are such monstrous, eternal hurricanes possible on Jupiter, but not on Earth? The answer lies in the fundamental differences between our planets. On Earth, storms are limited by the surface. When a hurricane reaches land, it loses its energy source, warm ocean water, and quickly dies. Mountains, continents, terrain irregularities, all of this breaks winds, breaks storms, dissipates energy. But Jupiter has no surface at all. It's a gas ball where atmosphere gradually transitions to liquid, where liquid transitions to superdense gas, and so on, layer after layer, all the way to the core. There are no obstacles. No mountains to break air streams. No oceans that end. There's only endless, uniform medium where winds can blow forever. Moreover, Jupiter receives energy not just from the Sun, though the Sun heats it weakly, 25 times weaker than Earth, but also from within. The planet releases more heat than it receives from the star. This is residual heat from the planet's formation 4.5 billion years ago. Gravitational energy released when compressing enormous masses of gas into one body was so immense that the planet is still cooling down. And this internal heat, rising from the depths, powers atmospheric dynamics, creating convection that never stops. That's why Jupiter's storms aren't weather in the Earth's sense. They're stable structures supported by constant energy flow from below and unimpeded circulation in the endless atmosphere. They can't disappear as long as the planet exists. They're part of it, as inseparable as Saturn's rings or their own moons. Now, when you've grasped the true scale of the planet itself, it's time to talk about what's happening on its surface. Or rather, not on the surface, because Jupiter has no solid surface, but in the upper layers of its atmosphere. We'll start with the most recognizable feature of Jupiter, its calling card, the object humanity has observed for over 350 years. The Great Red Spot. Again, forget everything you thought you knew about it. Because when you hear the word spot, your brain pictures something small, insignificant. A coffee stain on a shirt. A mud spot on a boot. Something you can wipe away with a rag. The Great Red Spot of Jupiter is not a spot. It's not a cloud. It's not just a weather phenomenon. It's an anticyclone. A giant, counterclockwise rotating storm that's been raging for at least 350 years, since Italian astronomer Giovanni Cassini first recorded it in 1665, and possibly for thousands more. Let's grasp the scale. The width of this spot is about 16,000 kilometers. Its length, over 40,000 kilometers, though it's gradually shrinking, but more on that later. If you could take our Earth, all of it, this huge world with its oceans, continents, mountains, and cities, and throw it into the center of the Great Red Spot, it would just drown there, like a coin in a whirlpool. It wouldn't touch the edges. There would still be enormous space for more raging winds around it. Moreover, you could take Earth, add Mars, and even 2 planets together would fit inside this storm with room to spare. But size is just the beginning. The real horror starts when you understand how old and constant it is. On Earth, the most powerful hurricanes, the ones that get names, the ones that destroy cities and take thousands of lives, last at most a few weeks. Usually a few days. Why? Because hurricanes feed on warm ocean water. Once a hurricane reaches cold water or land, it weakens and eventually dies from lack of energy. The Great Red Spot has been raging for more than 3.5 centuries. Think about it. When this storm was born, mammoths still roamed Earth, humans were just beginning to build the first cities, writing didn't exist, the wheel hadn't been invented, and this vortex was already spinning in Jupiter's atmosphere. It outlived all human civilizations. It witnessed the rise and fall of ancient Egypt. It was raging when Rome was founded. It endured the Crusades, world wars, the space race. And it continues to spin right now, at this very second, as you read these words. 350 years minimum. Possibly thousands. Tens of thousands. This isn't a hurricane. It's a geological structure expressed in gas movement. It's almost a living entity that feeds on energy from the planet's depths and doesn't care about human concepts of how long a storm should live. Now, about the wind speeds inside this monster. At the outer edges of the Great Red Spot, winds blow at 400 to 500 kilometers per hour. That's 1.5 times faster than Earth's most terrible hurricanes. Faster than bullets from some firearms. A speed at which air turns from invisible gas into solid weapon. Imagine standing at the edge of this storm. Impossible, but imagine. The wind wouldn't just blow strong at you. It would strike with force capable of tearing any material apart at the molecular level. If there were rock, it would be crushed to dust. If there were metal, it would be bent, twisted, and torn to pieces. But the most incredible thing isn't the wind speed. It's that this storm never stops. On Earth, the strongest hurricane lives a maximum of several weeks. Usually days. It's born over warm ocean water, gathers strength, reaches land, and dies there, losing its energy source. The Great Red Spot has been raging for over 3.5 centuries. Think about that. When this storm was born, Earth was still in the Age of Enlightenment. Isaac Newton hadn't yet written his laws of motion. Europeans hadn't fully discovered America. There was no electricity, no steam engines, not even an understanding that Earth revolves around the sun. And all this time, through wars, revolutions, rises and falls of civilizations, through all human dramas, there, in Jupiter's heavens, this red vortex spun, absolutely indifferent to our existence. The mystery of energy. Where does the fuel for an eternal storm come from? But here's what really stumps scientists. Where does the energy for this hurricane come from? On Earth, everything is clear. Hurricanes feed on ocean heat. Warm water evaporates, steam rises, condenses, releases latent heat of vaporization, which spins the vortex. Once the hurricane reaches cold surface or land, it starves to death. But Jupiter has no oceans. It has no solid surface. It only has layers of gas extending thousands of kilometers deep. So where does the Great Red Spot draw energy from to spin for centuries? The answer: from Jupiter's depths. The thing is, Jupiter isn't just a cold gas ball reflecting sunlight. It radiates its own heat. In fact, it radiates almost twice as much energy into space as it receives from the Sun. Where does this heat come from? First, it's residual heat from the planet's formation. When Jupiter was born 4.5 billion years ago, gravitational compression released colossal amounts of energy. The planet literally glowed like a small star. Since then, it has slowly cooled, radiating this ancient heat into space. Second, and this is even more interesting, inside Jupiter there's a constant process of gravitational differentiation. Helium, being heavier than hydrogen, slowly rains down to the planet's core, passing through layers of metallic hydrogen. This process releases additional gravitational energy, which turns into heat. Imagine a giant kettle that heats itself from the inside. Heat rises from the depths, creating powerful convective flows in the atmosphere. These flows feed storms, including the Great Red Spot. But here's the mystery. Why does this particular spot live so long while other storms on Jupiter are born and die within years or decades? The cannibalism theory, how a hurricane eats its own kind. Recent research conducted by the Juno probe, which now orbits Jupiter and takes detailed photos of its atmosphere, has revealed something shocking. The Great Red Spot may be a cannibal. Scientists notice that from time to time, smaller vortices and storms approach the edges of the giant anticyclone. And instead of bouncing off or breaking apart, they get pulled inside. The big storm literally consumes the small ones, taking their energy and mass. It's like a shark eating other fish to stay strong and large. Computer modeling shows that this mechanism could indeed support the existence of a giant vortex indefinitely, if there's enough food, that is, other storms and atmospheric disturbances. But here's what's interesting. The Great Red Spot is shrinking. When it was first observed in the 19th century with large telescopes, its size was about 40,000 kilometers in diameter, enough to fit 3 Earths inside side by side. Now it's only 16,000 kilometers. In a century and a half, the storm has shrunk more than in half. Moreover, the rate of shrinking is accelerating. In the 19th to 20th centuries, the spot shrank slowly, but in recent decades, the process has sped up. Does this mean the legendary storm is dying? That in a few decades or centuries, it will disappear completely? No one knows for sure. Perhaps it's a normal cycle. The spot shrinks, then grows again after consuming enough energy. Or perhaps we're living in an era where we're witnessing the slow death of one of the longest-lived weather phenomena in the known universe. Other storms, small monsters of Jupiter, but the Great Red Spot isn't Jupiter's only hurricane. In fact, the entire atmosphere of the planet is a boiling chaos with dozens, if not hundreds, of powerful storms. Look at detailed photos taken by the Juno probe from close range. What from a distance looks like calm bands of clouds up close turns into a mad labyrinth of vortices, eddies, whirlpools. There are storms the size of Earth. Storms the size of Mars. Storms that rotate clockwise, cyclones, and counterclockwise, anticyclones. White storms. These are rising cold ammonia clouds. Red and brown ones. These are chemical compounds created by photochemical reactions under ultraviolet light. In 2000, astronomers noticed something amazing. 3 white oval storms that had existed separately since the 1930s suddenly merged. In the process of merging, they changed color from white to red, much like their older brother. It was as if 3 small hurricanes combined into a mega-hurricane right before our eyes. Oval BA is now about half the size of the Great Red Spot, but still enormous, about 8,000 kilometers in diameter. And it continues to rage, live, and grow. Now let's talk about these famous bands, alternating light and dark belts encircling Jupiter parallel to the equator. These bands aren't just a pretty pattern. They reflect deep atmospheric processes. Light bands are called zones. These are high-pressure areas where gas rises from the depths, cools at high altitude, and ammonia clouds condense, creating bright, almost white color. Dark bands are called belts. These are low-pressure areas where gas descends, warms up, and clouds evaporate, revealing darker atmospheric layers. And here's what's important. Between neighboring belts and zones, wind speed can differ by hundreds of kilometers per hour. Imagine standing at a boundary. On one side, wind blows east at 500 kilometers per hour. On the other side, west at the same speed. Speed difference, 1,000 kilometers per hour. In a span of just a few tens of kilometers. This creates colossal turbulence. It's at these boundaries that the very storms are born, eddies caused by speed differences between neighboring currents. It's like two rivers flowing parallel but in opposite directions. Giant whirlpools form at their boundaries. Only here these aren't water rivers. These are gas rivers, each wider than all of Earth. Finally, the last but no less impressive phenomenon. Lightning. Oh yes, there is lightning on Jupiter. Lots of lightning. Very, very much. When Voyager 1 flew past the planet in 1979, it recorded flashes on Jupiter's night side. At first, scientists weren't sure what it was. Maybe starlight reflection? Maybe camera artifacts? But follow-up observations confirmed. It's lightning. Giant electric discharges slicing through the planet's atmosphere. How powerful are they? Typical Earth lightning releases about 1 to 5 billion joules of energy. That's enough to power a 100-watt light bulb for several months. Jupiter's lightning is thousands of times more powerful. Some discharges are so bright they can be seen even from the sunlit side of the planet, despite blinding solar light. These lightning bolts can stretch thousands of kilometers. They don't jump between cloud and ground, like on Earth, but between different cloud layers, piercing the atmosphere to enormous depths. One such lightning bolt could instantly incinerate an entire city. Turn it to plasma in a fraction of a second. But here's what's strange. There aren't as many lightning bolts on Jupiter as you'd expect from a planet with such an active atmosphere. On Earth, about 100 lightning strikes happen every second across the planet. On Jupiter, despite being 11 times larger in diameter and having a correspondingly larger area for storms, there are fewer. Why? One theory says Jupiter's lightning forms much deeper, where water can exist in liquid form, creating clouds of water droplets, like on Earth. But that depth, 50 to 100 kilometers below the visible cloud surface, is where conditions are so extreme that discharge formation is difficult. Nevertheless, when lightning does break through, it does so with apocalyptic force. In addition to everything else, here's one of the most beautiful and simultaneously terrifying phenomena on Jupiter. Auroras. You've seen Earth's northern and southern aurora? Those shimmering green and red curtains of light dancing in the high-latitude sky? Forget them. Compared to Jupiter's auroras, Earth's auroras are like a dim light bulb next to a stadium floodlight. Jupiter's auroras are larger than our entire planet. They glow constantly, without pause day and night, though during the day they're drowned out by reflected sunlight. Where does such power come from? All thanks to Jupiter's magnetic field, the most powerful planetary magnetic field in the solar system. It's 20,000 times stronger than Earth's. This field captures charged particles, electrons and ions, from the solar wind and from the volcanic moon Io, which we'll discuss later. These particles are accelerated by the magnetic field to enormous speeds and directed along field lines to Jupiter's poles. There they crash into the upper atmosphere with such force that the atmosphere begins to glow. Not just green or red, but across the entire spectrum, from ultraviolet to infrared radiation, with intensity millions of times greater than Earth's auroras. If you could see in ultraviolet, Jupiter would look like a giant lamp with two glowing disks at the poles that never go out. And here's what's particularly interesting. Part of this aurora is caused not by solar wind, but by Jupiter's moons. Io, The innermost large moon ejects tons of volcanic material into space every second. This material ionizes, gets captured by the magnetic field, and forms a giant plasma torus, donut, around the planet. When this plasma crashes into the atmosphere at the poles, it creates bright spots, footprints of each Galilean moon in the auroras. You can literally see the imprints of moons on the planet's atmosphere. But here's the irony. This bombardment, this rain of death from space, may have brought with it the ingredient without which there would be no life. Water. You see, young Earth forming in the inner, hot part of the system was relatively dry. Temperatures that were too high for ice to exist stably in the protoplanetary disk. Water evaporated and was carried away by the solar wind. But comets arriving from the outer, cold regions were filled with ice. Lots of ice. And organic compounds. When these bodies crashed into Earth, the ice instantly vaporized from the impact's heat, turned to steam, then cooled, condensed, and fell as rain on the cooling surface. Impact after impact, millions of impacts, billions of tons of water slowly accumulating on the surface of the young planet. And eventually this water filled depressions, creating oceans. A significant portion of the water in your oceans, the water you drink, that you're made of, was delivered by comets during the late heavy bombardment. This means the water in your body is older than life on Earth. It flew in from the cold outskirts of the solar system, survived destructive impacts, vaporized, froze, melted, and eventually became part of you. The giants that nearly destroyed us with their migration also gave us the oceans without which there would be no life. Now we move to the second gas giant, Saturn. If Jupiter is the king of gravity, Saturn is the king of beauty. Saturn is most famous for its rings. Those rings that make it instantly recognizable, that have become a symbol of space itself. But behind this beauty lies a harsh truth. For a long time, astronomers thought Saturn's rings were as old as the planet, 4.5 billion years. The remnant of the protoplanetary disk. But data from the Cassini mission, which orbited Saturn for 13 years, 2004 to 2017, shattered this theory. The rings are too clean, too bright, too perfect. If they were billions of years old, they'd be contaminated. Space dust, micrometeorites, comet debris, all of this falls on Saturn constantly. Over billions of years, the ice would darken, become gray-brown. But the rings shine like fresh snow. This means they're young. Very young. Scientists estimate Saturn's rings are only 100 to 200 million years old. Maybe even less. This means that when dinosaurs walked Earth, Tyrannosaurus, Triceratops, long-necked sauropods, Saturn had no rings. It was a bare, striped gas giant. And only relatively recently, when mammals were already dominating Earth, when primates were evolving, a catastrophe occurred there in the heavens. A moon died. A large ice moon came too close to Saturn, crossed the Roche limit, and was torn apart by tidal forces. The ice from that moon formed the rings we see today. If the rings are Saturn's signature for the public, then the hexagon at its north pole is what drives scientists mad. Imagine a hurricane at a planet's pole. A giant vortex. Nothing unusual, right? Jupiter has polar cyclones too. Now imagine this hurricane has the shape not of a circle, not an oval, but a perfect hexagon. With straight sides. With clear angles. This is not a camera artifact. This is not image processing. This is a real atmospheric structure on Saturn. The hexagon was first seen by the Voyager probes in the early 1980s. Scientists thought it was temporary. But when Cassini arrived 25 years later, the hexagon was still there. It hasn't moved. It hasn't changed. It rotates with the planet. Each side of the hexagon is about 14,000 kilometers long. That's larger than Earth's diameter. You could fit 4 Earths inside it, with room to spare. Winds of 300 to 400 kilometers per hour blow along its perimeter, creating a barrier that keeps clouds inside from mixing with the outside atmosphere. At the very center, exactly at the North Pole, a powerful cyclone rotates, the eye of the storm, 2,000 kilometers in diameter. How does nature create such rigid geometry? Long a mystery. Nature usually loves smooth lines, circles, spirals, not straight angles and hexagons. Lab experiments provided the answer. Scientists created a rotating cylinder of fluid with different speeds at different radii. At certain conditions, polygonal wave structures indeed formed: triangles, squares, hexagons. These are called Rossby waves, standing waves in the atmosphere created by the planet's rotation and wind speed differences at different latitudes. For some reason, on Saturn this wave stabilized as a hexagon and has remained stable for decades, perhaps centuries. The hexagon changes color with the seasons. Over Cassini's observations, it shifted from bluish to golden brown as Saturn's northern hemisphere tilted toward the Sun. But the shape, the geometric frame, remains. Saturn's hexagon is a reminder that planetary-scale hydrodynamics can create miracles that look intentionally designed, though they result from blind physical laws. Journey into the monster. What lies beneath the clouds? Now it's time to destroy another fundamental myth that's settled in people's minds since school. The myth that a gas giant is just a big, loose cloud you could fly through like a plane through fog. This myth is as dangerous as it is stupid. It completely ignores the physics of extreme states of matter that reign inside these planets. The word gas in the context of Jupiter means something completely different from what you're used to when inflating balloons or breathing air. Gas inside a giant planet behaves entirely differently because conditions there are extreme beyond human comprehension. Let's conduct a mental experiment. Imagine we, mad scientists, decide to test this gas ball theory in practice. We've built a super strong bathyscaphe from a non-existent material, because real materials wouldn't survive even a second, and we're heading straight for Jupiter's center. Our goal: reach the planet's core. Or find out if it exists at all. Strap in. This will be the most terrifying journey you've ever undertaken. Your journey begins in Jupiter's upper atmosphere, at an altitude where pressure equals Earth's 1 atmosphere. It's still relatively calm here. White clouds of ammonia ice crystals drift around you, fluffy, light, almost like Earth's cirrus clouds at high altitude. Though they consist not of water, but of toxic ammonia, which on Earth is used as cleaning solution and fertilizer. But visually, beautiful. Temperature here is minus 150 degrees Celsius. Very cold by Earth standards, but your bathyscaphe can handle it. Pressure is like sea level on Earth, 1 atmosphere. Everything is relatively tolerable so far. You descend lower. First 100 kilometers pass. Solar light still penetrates the thin haze. You see strange cloud structures, eddies, flows. If you had portholes, the view would even be beautiful. But now you descend deeper, and the first noticeable change occurs. Darkness falls. At 200 to 300 kilometers deep, solar light no longer reaches you. Layers of ammonia clouds above are too dense. You plunge into darkness, illuminated only by rare lightning flashes somewhere in the distance. This darkness isn't like night on Earth. It's absolute, total, oppressive darkness. You understand that above you lie thousands of kilometers of gas, and not a single ray of light will ever penetrate here. The thermometer shows minus 100 degrees. Pressure, already 5 atmospheres. That's like diving 40 meters underwater in Earth's oceans. Quite tolerable for technology. You keep descending. Another 100 kilometers pass. Temperature starts rising. Minus 50. Minus 30. 0. Plus 30. And here you pass through a layer of water clouds. Yes, there's water on Jupiter. Lots of water, in the form of vapor and ice crystals, at a depth of about 350 to 400 kilometers where pressure is 5 to 10 bars and temperature is close to Earth's values. If you could stop here, you'd find yourself at the only place on Jupiter where conditions even remotely resemble Earth's. Moderate temperature, water present. Some scientists have even suggested that some form of life could theoretically exist here. Microorganisms floating in clouds, feeding on chemical reactions. But you don't stop. You go deeper. And here the real madness begins. At about 500 to 1,000 kilometers deep, pressure reaches 100 atmospheres. Temperature is already plus 150 degrees Celsius. Your bathyscaphe groans, though it's made of fantastic material. You feel the environment around you becoming denser, thicker. Gas stops behaving like gas. It transitions into a state physicists call a supercritical fluid, something between gas and liquid. Let me explain what this means. On Earth, you have a clear boundary between gas and liquid. Water can be steam, gas, or liquid water. Between them is a phase transition. You can see steam condensing into droplets. There's a moment of transition. But if you take water and simultaneously heat and compress it, bringing it to temperatures above 374 degrees and pressures above 218 atmospheres, something strange happens. The boundary between gas and liquid disappears. The substance becomes a supercritical fluid. It's dense like a liquid but flowing and penetrating like gas. There are no bubbles, no surface, no splash when immersing. That's what happens to hydrogen on Jupiter at about 1,000 kilometers deep. It stops being gas but doesn't become liquid in the usual sense. It becomes something else. And you float or fly. The difference is erased through this medium. It becomes denser, thicker, more viscous, gradually, smoothly, without jumps. Pressure grows exponentially. 500 bar. 1,000 bar. 10,000 bar. Temperature is already 1,000 degrees Celsius. Outside your bathyscaphe is hotter than in a blast furnace. Any Earth material would have melted long ago. But you keep descending because there's still tens of thousands of kilometers to the core. And here, at about 10 to 15,000 kilometers depth, roughly Earth's diameter, you've descended a distance equal to passing through our entire planet. Something incredible happens. Pressure reaches 2 million atmospheres. 2 million. This means every square centimeter of your hull bears the weight of about 2 tons. On every square millimeter, 20 kilograms. Temperature, about 10,000 degrees Celsius. That's hotter than the sun's surface, 5,500 degrees. Under these extreme conditions, hydrogen, the simplest, lightest element in the universe, consisting of 1 proton and 1 electron, breaks down. Picture what happens at the atomic level. Normally, electrons orbit atomic nuclei on specific orbits. They're bound to the nucleus by electromagnetic force. Hydrogen atoms pair up to form H molecules. But when pressure becomes monstrous enough, the space between atoms collapses. Atoms are compressed so tightly that electrons can't stay on their orbits anymore. They're torn from their bonds. Electrons detach from nuclei and begin to move freely as a sea of negative charges between positive nuclei. You get a sea of protons, hydrogen nuclei, floating in an ocean of free electrons. And what is a metal by definition? A substance where electrons can move freely, conducting electricity. Metallic hydrogen is a real metal. It would shine, if anyone could see it in this darkness. It conducts electricity better than copper. It's denser than water but remains liquid due to colossal temperature. And there are oceans of this substance on Jupiter. Thousands, tens of thousands of kilometers thick. Scientists have tried for decades to create metallic hydrogen in labs. They compressed it between diamond anvils, bombarded it with lasers, creating pressures of millions of atmospheres for fractions of a second. They managed to create tiny samples that lasted microseconds. But on Jupiter, there's an entire ocean of this stuff, 30 to 40,000 kilometers deep. This ocean doesn't stand still. It flows. It boils. It rotates with the planet. The dynamo machine, birth of the magnetic field, and here's the magic that explains one of Jupiter's greatest mysteries. You see, liquid metallic hydrogen is an excellent conductor of electricity. Even better than copper. And when massive amounts of this conductive material move, rotate, form convective currents, hot rises, cold descends, they create electric currents. And moving electric currents generate magnetic fields. That's basic physics. Jupiter as a whole is a giant natural dynamo machine. An ocean of metallic hydrogen thousands of kilometers deep rotates, flows, creates currents, and these currents generate that monstrous magnetic field we observe outside. Picture the scale of this machine. A conductor larger than Earth, flowing, rotating, creating currents measured in billions of amperes. This is the largest electromagnet in the solar system. And you float through it. Through liquid metal, hot as a star's surface, dense as lead, flowing in darkness and creating invisible force lines that extend millions of kilometers into space. Your instruments are off the charts. Magnetic sensors go crazy. Temperature outside is already 15 to 20,000 degrees. Pressure, millions of atmospheres. And you still haven't hit bottom. For decades, scientists debated. Does Jupiter have a solid core? And if so, what is it like? The logic was simple. For a gas giant to form, there first had to be a solid seed, a chunk of rock and ice large enough to begin attracting gas through gravity. When such a core reaches about 10 Earth masses, it starts to avalanche capture hydrogen and helium from the surrounding protoplanetary disk. Gas falls onto the core, compresses, and a giant is born. Therefore, somewhere in Jupiter's center should be that primordial core. Rock, ice, iron, something solid. But no one could verify this hypothesis directly. You can't send a probe to Jupiter's center. It would be crushed in seconds. Only indirect methods remain. Studying the planet's gravitational field and trying to reconstruct its internal structure from how that field is distributed. Then in 2016, the Juno probe arrived at Jupiter with a special mission. To measure the gravitational field with unprecedented precision by flying low over the clouds in an elongated polar orbit. The data Juno sent back shocked the scientific community. It turns out there is a core. But not the one they expected. It's not solid. Not sharp. Not like a rocky ball in the center, like a peach pit. Jupiter's core is fuzzy, or diluted, as astrophysicists say, trying not to laugh at the absurdity of having to describe the center of a giant with the word fuzzy. What does this mean? Imagine throwing a sugar cube into hot tea. At first it's solid and dense. But then the edges begin to dissolve. The sugar becomes soft, porous. The boundary between sugar and water blurs. The center is still denser, but around it is a transitional zone where the sugar is partially dissolved. That's what Jupiter's core is like. Billions of years of extreme temperatures and pressures led to the rock and metal that made up the primordial core beginning to dissolve in the surrounding metallic hydrogen. The result is a huge zone of variable density, where heavy elements, silicon, iron, magnesium, oxygen, are mixed with hydrogen, creating a gradient from very dense center to less dense periphery. This zone may occupy up to half the planet's radius. This means Jupiter's core may be larger than Earth itself. Finally, you reach the very center. If you can call a fuzzy zone without clear boundaries a center. Temperature here is estimated to reach 30 to 35,000 degrees Celsius. Maybe even 40,000, no one knows for sure. For reference, the Sun's surface is 5,500 degrees. Jupiter's core is 5 to 6 times hotter than the Sun's surface. Pressure, about 40 to 45 million atmospheres. Millions. Under such conditions, the concepts of solid, liquid, or gaseous lose meaning. Matter exists in an extreme state that we cannot reproduce in Earth labs. It's plasma compressed to rock density. It's rock heated to plasma state. It's something in between, for which we don't even have a name. Quantum effects begin to matter. Electrons are pressed into nuclei so tightly that their wave functions overlap. Atoms exist in states not described by classical physics. This is a place humanity will likely never reach. Not in the next 100 years. Not in the next 1,000. Maybe never. Because even if we someday create materials that can withstand such pressure and temperature, which itself seems impossible, we'd still have to pass through thousands of kilometers of radioactive hell, metallic ocean, supercritical fluid. Jupiter's heart is a heart of darkness. The hottest, densest, most inaccessible place in Earth's vicinity. A place where pressure and temperature turn matter into something alien. And this heart holds up the entire planet. Its gravity prevents the gas from flying into space. Its heat, slowly leaking outward, Jupiter radiates more energy than it receives from the Sun. It's still cooling from formation 4.5 billion years ago, fuels eternal storms in the upper atmosphere. So every time you look at Jupiter's bands and great red spot, remember, you're seeing only the thinnest skin of the beast. Its true face, its real nature lies hidden under thousands of kilometers of liquid metal, in a world where surface and solidity lose all meaning. This isn't a planet in the usual sense. It's a gradient of pressure, temperature, and density stretched 70,000 kilometers deep. It's a monster existing on the boundary between planet and star. One that almost became a star but didn't have enough mass. And it's this monster, with its ocean of metallic hydrogen, its fuzzy core of dissolving rock, its Earth-sized storms, that plays a key role in our world's fate. But more on that later. For now, we need to talk about Jupiter's court. Its moons. Entire worlds that orbit the giant-like planets around a star. The Galilean moons, 4 full-fledged worlds at the giant's feet. Jupiter is so enormous and powerful that it doesn't travel alone. An entire army of moons orbits it, 95 confirmed objects as of today. But most of them are just captured asteroids, shapeless rocks the size of cities or mountains, flying along strange, elongated orbits. However, among this crowd are 4 true giants, 4 full-fledged worlds that, if they orbited the Sun instead of Jupiter, we would undoubtedly call planets. These are Io, Europa, Ganymede, and Callisto, the Galilean moons, named after Galileo Galilei, who first saw them through his homemade telescope on a cold January night in 1610. And this discovery changed everything. You see, before Galileo, people believed everything in the universe revolved around Earth. Sun, moon, planets, stars, all circled us because we were the center of creation. This wasn't just a scientific theory, it was religious dogma backed by church authority. And then Galileo aimed his primitive telescope, giving only 20x magnification. Modern amateur telescopes give 100-200x, at a bright dot in the night sky, Jupiter, and saw 4 tiny stars next to the planet. At first he thought they were background stars. But the next night he looked again, and they had moved. They changed position relative to Jupiter. After a few nights of observation, it became clear. They orbited the planet. Not Earth. Jupiter. This was a death blow to the geocentric model. If objects existed that clearly didn't orbit Earth, then Earth wasn't the center of everything. Then Copernicus was right. Then we weren't the crown of creation, but just one of the planets. Galileo published his discovery in March 1610 in a small book called Starry Messenger. The book shocked the scientific world and enraged church circles. Ultimately, this discovery, along with other observations, led to Galileo being called before the Inquisition, forced to recant his views, and kept under house arrest for life. But the truth had been set free. And those 4 tiny points of light Galileo saw through his crude tube played a key role in the scientific revolution that overturned humanity's understanding of its place in the universe. Now let's get to know these worlds better. Because each of them is a separate story, a separate nightmare, a separate miracle. Let's start with Io, the closest large moon to Jupiter. And this is, without exaggeration, the most volcanically active body in the solar system. Not a bit more active than Earth, but millions of times more. Imagine a world that looks like a rotten orange or pepperoni pizza. Yellow-orange surface covered in dark red, brown, and white spots. No craters. They simply don't exist because any crater fills with fresh lava before it can age. Instead, there are hundreds of active volcanoes. Io is the most volcanically active body in the solar system. And this isn't just a statement, it's an attempt to describe absolute hell. At any given moment, an average of several dozen volcanoes erupt simultaneously on Io. Some eject lava in fountains 300 to 400 kilometers high. 300 kilometers. For comparison, the International Space Station orbits at 400 kilometers. Volcanoes on Io blast molten rock to orbital altitude. Why is Io so furious? Because it's caught in gravitational vice grips. On one side, massive Jupiter pulls it. On the other, neighboring large moons Europa and Ganymede, which are in orbital resonance with Io. This means they regularly line up in a specific configuration and yank Io with their gravity. What happens? Io is constantly stretched and compressed. Its shape changes. The solid crust rises and falls by hundreds of meters, like a wave. And this happens constantly, endlessly, without stop. Imagine taking clay and kneading it in your hands. Stretching, compressing, twisting. What happens? The clay heats from friction. Now imagine doing this with a moon the size of our own, and doing it for billions of years without stopping. Io's interior is melted. There's an ocean of magma dozens, maybe hundreds of kilometers deep. And this magma constantly seeks escape, bursting through cracks in the crust in giant eruptions. When Voyager 1 first sent back images of Io in 1979, scientists couldn't believe their eyes. They saw volcanic eruptions in real time on photographs. Huge plumes of sulfur and sulfur dioxide rising above the surface to heights greater than the moon's radius. One of Io's most powerful volcanoes is named Loki, after the Norse god of chaos and deception, an appropriate name. It's not just a volcano, it's a lava lake more than 200 kilometers across. Imagine a lake of molten rock larger than Moscow. It constantly boils, its surface constantly renews. Temperature, around 1,300 degrees Celsius. If you could stand on Io, impossible. Radiation would kill you, temperature would kill you, the toxic sulfur dioxide atmosphere would kill you. You'd see a horizon dotted with glowing volcanic points. The sky would be yellow-green from sulfur emissions. Overhead, giant Jupiter would occupy half the sky. And the ground underfoot would constantly shake from volcanic tremors. This is hell. Literally. A world of fire, sulfur, and endless eruptions. And the scariest part? Io can't stop. As long as it remains in orbital resonance with Europa and Ganymede, as long as Jupiter keeps kneading it with gravity, volcanism will continue. For millions, billions of years. Forever. Now we move slightly farther from Jupiter, to the next large moon, Europa. Here we transition from fire to ice, from hell to, well, to hope. Europa looks like a perfectly smooth ice ball. One of the smoothest objects in the solar system. Its surface has almost no mountains, no deep depressions. But it has a network of cracks, fractures, lines that crisscross the entire surface like veins on a hand or cracks on a frozen lake. This association with a frozen lake is most accurate. Because Europa is exactly a frozen lake. Or rather, a frozen ocean. A huge, global ocean of liquid water hidden under an ice crust 15 to 25 kilometers thick. Under that ice, in complete darkness, splashes an ocean 100 to 150 kilometers deep. For comparison, the deepest point in Earth's ocean, the Mariana Trench, is only 11 kilometers. Europa's ocean contains twice as much water as all of Earth's oceans combined. Think about that. A small moon, smaller than our moon, holds more water than Earth's entire surface. And most importantly, this water is liquid, not ice. Liquid water at temperatures around 0 or slightly above, where fish could theoretically swim, if they existed there. Where does the heat to keep this ocean liquid come from? The same source as on Io, from tidal heating. Europa is also in orbital resonance, also needed by Jupiter's gravity, though not as strongly as Io. So instead of volcanoes, it just has warm water under ice. And here's where it gets most interesting. Because liquid water is the main ingredient for life as we know it. And if there's water, if there's heat, if there are chemical elements, and they are definitely there, salts, minerals from the rocky seafloor dissolve in the ocean, if there are energy sources, then why couldn't there be life? On Earth, we found life in the most unexpected places. At the ocean floor, near hydrothermal vents where water boils at 400 degrees, where pressure would crush a human like a tin can, there are creatures. Bacteria, worms, shrimp, crabs, entire ecosystems that don't depend on sunlight, that feed on chemical energy from Earth's depths. If this is possible here, why not on Europa? Imagine a dark ocean under an ice shell. On the seabed, hydrothermal vents where hot water heated by tidal friction in the moon's depths seeps through cracks in the rocky floor. Around these vents, oases of life. Microorganisms feeding on chemical reactions. Perhaps more complex creatures similar to our deep-sea worms or jellyfish. Maybe right now, as you read these words, something is swimming in Europa's dark waters. Something blind, slow, feeding on the planet's chemical breath. Something that has never seen light, knows nothing of the sun, stars, or us. Scientists dream of sending a probe there. Not just flying past, but landing on the ice, drilling, or finding a natural crack, lowering a submarine into the ocean and exploring it. This would be the most important mission in human history, because if we find even one bacterium there, it would mean life isn't a unique miracle of Earth, but a common phenomenon in the universe. NASA is planning the Europa Clipper mission, scheduled to launch in 2024. The probe will fly by Europa dozens of times, study the ice shell, look for places where water might be ejected into space, such geysers have possibly been detected, analyze their composition. Then, if all goes well, in 20 to 30 years we might send a lander. And then the real hunt will begin. Europa isn't just an ice ball. It's humanity's greatest hope for finding extraterrestrial life without leaving the solar system. The third in our list, Ganymede. And it deserves special mention for one simple reason. It's the largest moon in the solar system. Period. Ganymede's diameter is 5,268 kilometers. That's larger than Mercury, 4,879 kilometers. That's larger than Pluto, 2,377 kilometers. Ganymede is a full-fledged world, just sentenced to orbit a larger body. If it orbited the Sun instead of Jupiter, we would undoubtedly call it a planet. And it has one unique feature no other solar system moon possesses: its own magnetic field. Think about what this means. A magnetic field is generated by moving liquid metal inside a celestial body, as we discussed with Jupiter. Earth has a magnetic field because we have a liquid iron core. Mars doesn't. Its core cooled and solidified billions of years ago. Ganymede, a moon, has one. This means it has a liquid iron core inside that is still hot and mobile. It behaves like a mini-planet, with its own internal dynamics. Moreover, like Europa, Ganymede has a subsurface ocean. Yes, another one. An ocean of salty water about 100 kilometers deep, hidden under an ice crust 150 kilometers thick. Only unlike Europa, Ganymede's ocean is much deeper, and reaching it will be harder. But the fact of its existence is astounding. It turns out Jupiter has at least 2 moons with liquid water beneath the surface. 2 potential biospheres. Ganymede's surface is a patchwork of dark ancient areas covered in craters and light young areas crisscrossed by grooves and ridges. These are traces of tectonic activity from billions of years ago, when the moon's interior was more active. In short, Ganymede is an entire planet, just stuck orbiting another, larger planet. If fate had been different, if 4.5 billion years ago Ganymede had formed a bit farther from Jupiter, where the giant's gravity couldn't capture it, it would have become a full member of the planetary system. It would have its own name, its own orbit around the sun, its own place in textbooks. But instead, it's a moon. The largest, most impressive, but still a moon. Finally, Callisto, the 4th and most distant of the Galilean moons. It's at a safe distance from Jupiter, outside orbital resonance with other large moons, and thus has a completely different fate. Callisto is old. Ancient, scarred, tired old man who has seen everything. Its surface is the most cratered in the solar system. There are so many craters there that they overlap each other. Every square kilometer is pitted with asteroid and comet impacts. A new crater can't be made without destroying an old one. This means Callisto's surface is incredibly ancient. It's 4 billion years old. It remembers the era of the late heavy bombardment, when the entire solar system was like a shooting range where objects hurled rocks the size of cities at each other. Callisto doesn't participate in orbital resonance. It isn't heated by tides. It simply slowly cools, freezes, turning into a dead ice world. Under its crust, there may also be an ocean, data hint at this. But it's very deep, under hundreds of kilometers of ice, and there's likely not enough heat to support an active environment. Callisto is a cosmic archive, a silent witness to the early history of the solar system. Its craters are records of impacts that occurred billions of years ago. By studying them, scientists can reconstruct how intense the bombardment was, where objects came from, how their frequency changed over time. It's not the most exciting moon of the 4. It doesn't erupt like Io. It doesn't hold hope for life like Europa. It doesn't have a magnetic field like Ganymede. But it's important, because it remembers. And in its scars is written the history of our cosmic home. Saturn, Lord of the Rings and Master of Winds. If Jupiter is the ruthless king, the monster of power and gravity, then Saturn is the aristocrat. Elegant, refined, adorned with the most recognizable rings in the entire universe. When Galileo first aimed his telescope at Saturn in 1610, the same year he discovered the Galilean moons, he saw something strange. The planet looked triple, with 2 small airs on the sides. His telescope wasn't powerful enough to resolve the rings. He saw them as 2 strange protrusions. Galileo was puzzled and even published an anagram describing his discovery to reserve priority, but not reveal details until he figured out what they were. Only 45 years later, in 1655, did Dutch astronomer Christian Huygens finally understand. They were rings. A flat structure encircling the planet. Since then, Saturn has become a symbol of cosmic beauty. Its image, rings tilted toward the viewer, has become an icon recognizable even to people who know nothing about astronomy. But behind this beauty lies a harsh truth. For a long time, astronomers were confident that Saturn's rings were as old as the planet, 4.5 billion years. Remnants of the protoplanetary disk from which the forming giant planet emerged. Something that couldn't form into a moon due to tidal forces, and so remained as an eternal ring. It was a romantic, beautiful theory. The rings as a monument to the planet's birth, existing since the beginning of time. But then the Cassini mission arrived. 13 years Cassini orbited Saturn, studying the planet, rings, and moons. In the final phase of its mission in 2017, it made a series of daring dives between the rings and the planet, in the narrow gap where no one had ever flown. And the data it collected there shattered the old theory. The rings are too clean, too bright, too perfect. If they had existed for billions of years, they would have darkened. Space dust, micrometeorites, comet debris, all of this constantly falls on Saturn. If it falls on the planet, it inevitably falls on the rings too. Over billions of years, the ice would darken, become gray-brown, like the moon. But Saturn's rings are white. Dazzlingly white. They reflect almost all light that hits them, like fresh snow. This can only mean they are young. Incredibly young by cosmic standards. Estimates vary, but most scientists agree the rings are no more than 100 to 200 million years old. Possibly even less, 10 to 100 million years. Wait. Stop. Read that again. 100 million years. For reference, dinosaurs went extinct 66 million years ago. This means that when T-Rexes and Triceratops walked Earth, Saturn may have had no rings. It was a bare, striped gas giant. Only relatively recently, when mammals already dominated Earth, when primates were evolving, did a catastrophe occur in the heavens that gave Saturn its famous crown. What kind of catastrophe? The most likely version sounds like a murder story. Saturn had a large ice moon. Scientists named it Chrysalis. This moon orbited relatively close to the planet. Then, either due to collision with an asteroid or due to orbital resonance with other moons, Chrysalis came too close to Saturn. There is something called the Roche limit, the invisible boundary around any massive body where tidal forces, the difference in gravitational pull on the near and far sides of an object, becomes stronger than the object's own gravity holding it together. Cross this boundary, and you're torn apart. Chrysalis crossed it. Imagine what happened. The moon, perhaps the size of Mimas, about 400 kilometers in diameter, or even larger, slowly, inexorably approached the fatal line. First, cracks appeared. Huge fractures crossing the surface. Chunks of ice broke off and drifted away. Then the moon began to stretch, like dough in a baker's hands. And finally, the final rupture. The moon literally fell apart. First into large fragments. Then these fragments split further, and further, and further. The rocky core of Chrysalis, denser and heavier, fell into Saturn's depths and disappeared forever. But the light ice mantle remained in orbit. Over several thousand years, gravity and collisions spread these fragments into a thin, flat disk. Particles collided, broke apart, mixed, aligned into circular orbits. And thus the rings we see today were born. And here's what's amazing. Saturn's rings aren't a uniform structure. They're an incredibly complex, finely tuned system of thousands of individual ringlets, gaps, waves, and resonances. The main rings are labeled with letters in order of discovery. D, C, B, A, F, G. Among them, the brightest and most massive are rings A and B, separated by the Cassini division, named after the same Cassini who discovered them. Ring B is the densest and brightest. It contributes the most to Saturn's recognizable appearance. But even within each main ring are thousands of thin ringlets, dozens of gaps. Some gaps are created by small shepherd moons whose gravity clears a path, throwing particles out of certain zones. Others result from orbital resonances with larger moons like Mimas or Enceladus. The entire ring system spans about 280,000 kilometers from the inner edge of the main rings to the outer edge. That's 70% of the distance from Earth to the Moon. A huge structure. But here's what's truly insane. The thickness. In some places, the rings are only 10 meters thick. 10 meters! On average, about 1 kilometer. The thickness to diameter ratio is about 1 to 280,000. If you made a model of the rings the size of a football field, 100 meters in diameter, their thickness would be less than 1/3 of a millimeter. Thinner than a sheet of paper. This is the flattest natural structure known to science. But this beauty has an expiration date. The rings aren't eternal. They slowly, inexorably die. Two processes kill the rings. First, Saturn's gravity slowly pulls ring particles inward, especially small particles that are slowed by remnants of atmosphere at the ring's inner edge. They spiral inward and eventually enter the planet's upper atmosphere, where they evaporate. Second, Saturn's magnetic field charges ice particles, turning them into ions. These charged particles then move along magnetic field lines and also fall into the atmosphere, but at high latitudes, near the poles. The result is constant ring rain, showering Saturn with tons of water ice every second. Cassini measured this rain's intensity. Estimates show the rings lose about 10 tons of material per second. That sounds like a lot, but the rings are enormous. Their total mass is estimated at 15 to 30 million billion tons, half the mass of Mimas. Nevertheless, even with this colossal mass, in 100 to 200 million years the rings will disappear. Melt away. Fall as rain onto the planet. This means we, humans, Homo sapiens, a species existing for only 300,000 years, are unbelievably lucky to live right now. In this brief golden age when the rings exist. When we can see them with our own eyes, photograph them, study them. If we had appeared 200 million years later, we would never know Saturn once had rings. We'd see just a yellowish ball with cloud bands and think it had always been that way. Saturn's rings are not an eternal monument. They're a beautiful echo of a recent, in cosmic terms, catastrophe. The remains of a dead moon, temporarily adorning its killer. A reminder that in space, nothing lasts forever. Even the most monumental, most beautiful structures are born, live, and die. If the rings are Saturn's public signature, then the hexagon at its north pole is what drives scientists insane. Imagine a hurricane at a planet's pole. A giant vortex. Nothing unusual, right? Jupiter has polar cyclones too. Now imagine this hurricane has the shape not of a circle or oval, but a perfect hexagon. With straight sides. With clear angles. This isn't Photoshop. This isn't an image processing artifact. This is a real atmospheric structure on Saturn. The hexagon was first seen by Voyager probes in the early 1980s. Scientists thought it might be temporary or a camera artifact. But when Cassini arrived 25 years later, the hexagon was still there. It hasn't moved. It continues to rotate with the same speed as the planet. Each side of the hexagon is about 14,000 kilometers. That's larger than Earth's diameter, 12,700 kilometers. 4 Earths could fit inside it, with room to spare. Inside this giant geometric figure, winds blow at 300 to 400 kilometers per hour, creating a barrier that prevents clouds inside from mixing with the outside atmosphere. At the very center, exactly at the North Pole, a powerful cyclone rotates, the eye of the storm, about 2,000 kilometers in diameter. How does nature create such rigid geometry? Long a mystery. Nature usually loves smooth lines, circles, spirals. Not straight angles and hexagons. Lab experiments provided the answer. Scientists at Oxford created a rotating cylinder of fluid with different speeds at different radii. At certain conditions, polygonal wave structures indeed formed, triangles, squares, hexagons. These are called Rossby waves, standing waves in the atmosphere created by the planet's rotation and wind speed differences at different latitudes. For some reason, on Saturn this wave stabilized as a hexagon, and has remained stable for decades, perhaps centuries. The hexagon changes color with the seasons. Over Cassini's observations, it shifted from bluish to golden brown as Saturn's northern hemisphere tilted toward the Sun. But the shape, the geometric frame, remains. Saturn's hexagon is a reminder that planetary-scale hydrodynamics can create miracles that look intentionally designed, though they result from blind physical laws. Ice giants, Uranus and Neptune, worlds of paradoxes after Jupiter and Saturn. You might think you understand gas giants, and that beyond them are just smaller copies, a bit smaller, a bit colder, a bit farther. But here space delivers another blow to the solar plexus. Because Uranus and Neptune aren't just smaller gas giants. They're an entirely different class of planets where the word gas becomes almost inapplicable, and the term ice sounds like mockery given that temperatures inside reach tens of thousands of degrees. When astronomers say ice giants, they mean composition, not temperature. Ices refer to volatile compounds, water, ammonia, methane, as opposed to rocks, silicates, metals, and gases, hydrogen, helium. But inside these planets, under monstrous pressure and high temperature, these ices behave nothing like the ice in your freezer. Inside Uranus and Neptune, water, ammonia, and methane become hot, dense, ionized liquids that flow, conduct electricity, and behave completely unlike familiar substances. They're more like molten metal than ice. Uranus stands out among all solar system planets with one incredible feature. It rotates on its side. Uranus's rotation axis is tilted 98 degrees relative to its orbital plane. This means the planet essentially rotates like a barrel rolling along its orbit, not like a top spinning upright. The consequences are dramatic. If you're at Uranus's pole, you can observe a continuous day lasting 42 Earth years. The Sun slowly circles the horizon, never setting. Then comes continuous night, another 42 years of total darkness. At the equator, the situation is no better. There the Sun rises and sets, but its path across the sky is insane. At certain times of year, the Sun rises in the north, passes through the zenith, and sets in the south. Then, years later, it rises in the south and sets in the north. Seasons as we know them lose meaning here. What could tip an entire planet? The most likely explanation is a catastrophic collision. In the early solar system, Uranus was hit by an Earth-sized or larger object. The impact gave the planet a huge angular momentum, essentially knocking it over. Uranus survived. Gas and ice giants are hard to destroy by collision. They absorb the impact and redistribute energy throughout their volume. The result: a planet with a 98-degree axial tilt, forever bearing the scar of that ancient catastrophe. Now move even further, to the last giant, Neptune, 30 times farther from the Sun than Earth. At this distance, the Sun looks like just a bright star, providing 900 times less light and heat than on Earth. Logic suggests freezing cold, eternal darkness, calm. But Neptune defies logic. Because Neptune has the fastest winds in the solar system. Up to 2,100 kilometers per hour. 2,100 kilometers per hour. That's nearly twice the speed of sound in air. Faster than Jupiter's winds, faster than Saturn's, faster than Earth's most destructive tornadoes. And this on a planet receiving 900 times less solar energy than Earth. Where does such fury come from? Neptune, like other giants, radiates more heat than it receives from the Sun, 2.6 times more. This internal heat, rising from the depths, creates powerful convective currents. With no solid surface to break them, they accelerate to monstrous speeds. Neptune is also dotted with giant storms. The most famous, the Great Dark Spot, seen by Voyager 2 in 1989. An Earth-sized anticyclone, similar to Jupiter's Great Red Spot, but dark blue. When Hubble looked at Neptune years later, the spot was gone. Vanished. Other dark spots have appeared in other locations since. Neptune's storms are short-lived, unlike Jupiter's. They form, live a few years, then die. The atmosphere constantly tries different configurations, never finding stability. This at the edge of the solar system, in eternal cold and darkness. Now, about the most fascinating and almost fantastical phenomenon that scientists believe occurs inside Uranus and Neptune. Diamond rain. Not a metaphor. A real physical process predicted by theory and partially confirmed by experiments. Here's how it works. Methane in Uranus and Neptune's atmospheres, at depths of thousands of kilometers, under immense pressure and temperature, breaks down. Hydrogen escapes, carbon remains. And at pressures of millions of atmospheres and temperatures of thousands of degrees, carbon crystallizes into its densest form, diamond. Tiny diamond crystals form, then grow larger, become heavier, and begin to fall. They sink through layers of increasingly dense, hot material, slowly descending to the planet's core over millions of years, like hail falling through a storm cloud. Only this hail of diamonds can be the size of raindrops, or nuts, or fists. And they accumulate near the core, possibly forming entire layers of diamonds. Lab experiments confirm this. Scientists recreated conditions similar to ice giants' interiors using powerful lasers and shock waves. They took polystyrene, plastic rich in carbon and hydrogen, an analog of hydrocarbon mixtures, and compressed it with laser pulses. Pressure reached millions of atmospheres. Temperature, thousands of degrees. And what happened? Nanodiamonds formed. Tiny diamond crystals that could be detected by X-ray diffraction. This proves the process is possible. And if it's possible in a lab, it almost certainly happens inside planets where conditions are even more extreme and have lasted for billions of years. Inside Uranus and Neptune, there may be a constant diamond rain. Tons of diamonds may fall every second, accumulating in the depths. But it's impossible to reach them. This treasure is forever buried under thousands of kilometers of boiling, compressed matter. The Great Migration. When planets change orbits. When you look at a diagram of the solar system with planets neatly arranged on their orbits, Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, you get a sense of order. That it was always this way and always will be. But this is an illusion. Because planets aren't nailed to space. Their orbits aren't painted with indelible ink. Planets are bodies moving under gravity. And gravity isn't a static force, but a dynamic game of attractions and repulsions that can change orbits. And in the early solar system, these changes weren't gentle adjustments, but catastrophic rearrangements. One of the most dramatic theories about the early system is called the Grand Tack. The term comes from sailing, where a tack is a maneuver where a ship sharply changes direction. Here's what supposedly happened. About 4.5 billion years ago, when planets were just forming, Jupiter wasn't born where it is now. It was closer to the Sun, roughly at Mars's current orbit, 1.50. And it began migrating inward, pulled by interaction with the gas disk that still surrounded the young Sun. Jupiter was moving inward, like a heavy ship sailing upwind. And in its path lay the zone where rocky planets were forming, future Mercury, Venus, Earth, Mars. If Jupiter had continued, it would have physically swept away, scattered, and ejected all the building material for these worlds. The inner solar system would have become a wasteland. But then Saturn got involved. While Jupiter migrated inward, Saturn was growing behind it. And when Saturn gained enough mass, it also began interacting with the gas disk. And then came the critical moment. Jupiter and Saturn entered orbital resonance. Their orbital periods synchronized in a 2-to-1 ratio, or 3-to-2, exact details are still debated. They began moving in lockstep. Then something incredible happened. The bound pair of giants, acting in unison, could change migration direction. Saturn, with its gravity, like a tugboat, caught Jupiter and pulled it back outward. The disk that once dragged Jupiter inward now began pushing it outward. Jupiter turned around and began migrating back outward, toward the system's edges. Astronomers call this Grand Tack. And this turn saved the inner system. Jupiter moved back out, leaving chaos behind, but also opportunity. Planet embryos that survived could continue growing. Earth could form. The price was paid. Mars was shortchanged. Jupiter, passing through its formation zone, threw out or scattered most building material, and Mars remained small, underfed. But Earth got its chance. And billions of years later, life appeared on this planet, civilization, all because Jupiter turned around. Because Saturn was in the right place at the right time. Because gravity and orbital mechanics aligned just so. But the giants' migration had consequences for the outer system too. When Jupiter and Saturn rearranged their orbits, their gravity rippled through the outer regions where ice giants formed and where huge reserves of icy bodies lay, the future Kuiper Belt and Oort Cloud. This gravitational wave knocked billions of ice chunks from their stable orbits. Some flew into interstellar space. Some were captured by giants. But many, very many, flew inward, straight toward the sun. And on their way were the young rocky planets. Thus began the late heavy bombardment. About 4.1 to 3.8 billion years ago, the inner solar system became a shooting gallery. Mercury, Venus, Earth, Mars, the Moon, all were subjected to intense bombardment by comets and asteroids. The impacts came one after another for hundreds of millions of years. The Moon is cratered. The dark spots on its disk are lava seas that filled giant impact basins created during this bombardment. Each impact released energy equivalent to millions of atomic bombs. It melted crust, vaporized mountains, created shockwaves that rolled across the entire planet. Young Earth was cratered. But unlike the Moon, Earth has a young surface, constantly renewed by tectonics, so traces of that era have been erased. But it happened. And it was terrifying. But here's the irony. This bombardment, this rain of death from space, may have brought the ingredient without which there would be no life. Water. You see, the young Earth forming in the inner, hot part of the system was relatively dry. Temperatures were too high for ice to exist stably in the protoplanetary disk. Water evaporated and was carried away by solar wind. But comets arriving from the cold outer regions were filled with ice. Each comet is a dirty snowball of frozen water, ammonia, methane mixed with dust. When such a comet hit Earth, the ice instantly vaporized from impact heat, then cooled, condensed, and fell as rain on the cooling surface. Millions of impacts. Millions of water deliveries. Over hundreds of millions of years. Eventually, this water filled depressions, creating oceans. A significant portion of the water in your oceans, the water you drink, that you're made of, was delivered by comets during the late heavy bombardment. The catastrophe orchestrated by migrating giants became a necessary condition for life. Without Jupiter and Saturn's migration, there would have been no bombardment. Without bombardment, there would be no oceans. Without oceans, there would be no life. We exist because giants danced in the young solar system, creating chaos. And this chaos, blindly, accidentally, created conditions for us. Conclusion. Living in a narrow crack between catastrophes now that the whole story has been told, it's time to step back and comprehend it all. The gas and ice giants aren't somewhere out there on the system's outskirts. They're woven into Earth's fate as tightly as oxygen in the air. Jupiter almost destroyed us with its migration, but turned at the last moment. Saturn helped to turn, possibly saving the inner system. Uranus and Neptune, thrown outward, initiated the bombardment that brought water. Now the giants stand on their orbits, silent, huge, indifferent. They continue to slowly influence the system with their gravity. They continue to intercept some comets, preventing them from reaching us. But sometimes they throw those comets our way. We live in a narrow crack between destruction and creation. In a window of opportunity that opened accidentally and may close just as accidentally. We live in a narrow gap between catastrophes. In a window of possibilities that opened by chance and may close by chance just as easily. The stability of our system is temporary. Orbits slowly change. Over millions, tens of millions of years, the configuration may shift. Perhaps Mercury will be ejected. Perhaps Earth's orbit will shift. We don't know. But we know that in space, eternal peace doesn't exist. We exist in a brief moment when the giants are at a sufficient distance, when their orbits are sufficiently stable, when the inner system receives protection but not destruction. This window may close. Not tomorrow, not in 1,000 years, but someday. Call to gratitude so when you next look at the night sky and see the bright point of Jupiter or the faint glow of Saturn, remember this story. Remember that these distant worlds aren't just beautiful cosmic decorations. They are the architects of our destiny, creators and destroyers simultaneously, giants that nearly killed us but ultimately gave us life. Say thank you to them for stopping, for turning around, for allowing us to exist in this fragile, temporary, incredibly lucky point in space and time. Space Missions, The Heroic Journey to Giants, Extended Edition. Before any spacecraft dared approach Jupiter, astronomers could only guess what awaited them. The gas giant was a cosmic fortress guarded by invisible walls of radiation, magnetic fields, and gravitational traps that could tear apart anything that came too close. Yet humanity did something unprecedented. We sent 4 probes to their near-certain doom, not to survive, but to see before dying. The Pioneer 10 and Pioneer 11 missions, launched in 1972 to 73, were humanity's first reconnaissance scouts, built with 1970s technology, carrying less computing power than a modern toaster, tasked with flying past Jupiter and Saturn and surviving long enough to whisper back what they saw. Engineers knew radiation would be fierce, but they underestimated its intensity by a factor of 10. Pioneer 10's trajectory brought it within 130,000 kilometers of Jupiter's cloud tops, close enough to taste the poison. Almost immediately, its circuits began to fry. The imaging photopolarimeter failed. The plasma analyzer glitched. Data streams became corrupted, filled with phantom signals from dying electronics. It was like sending a baby into a nuclear reactor and hoping it would send a postcard before melting, one mission's scientists later admitted. Pioneer 10 did send its postcard, a blurry, low-resolution image showing Jupiter not as a peaceful marble, but as a boiling cauldron with faint hints of the Great Red Spot. Then, 3 months after the flyby, its signal began to fade. Not from distance, but from cumulative radiation damage. By 2003, Pioneer 10 fell completely silent, its final transmission a ghost whisper from 12 billion kilometers away. Pioneer 11 fared slightly better. Using Pioneer 10's data, engineers redesigned shielding, adding layers of tantalum and aluminum to protect critical components. It survived Jupiter's flyby in 1974, then a daring slingshot to Saturn in 1979, becoming the first human artifact to touch the ring giant. Yet even with upgrades, Pioneer 11 suffered. Its power supply degraded. Its instruments failed one by one. In 1995, it too went dark. Both pioneers proved one terrifying truth. The outer planets were not passive giants, they were active killing fields. Every subsequent mission would have to be built like a tank, armored against radiation storms that could cripple electronics in seconds. If the pioneers were scouts, the Voyager twins, 1977, were full-scale invasions. Funded as a once-in-175-year planetary alignment opportunity, these 722-kilogram probes carried the most sophisticated instruments ever built, and a golden record with sounds of Earth, just in case something out there was listening. Voyager 1's encounter with Jupiter in March 1979 was a revelation. Its cameras were 100 times better than Pioneer's. It saw the Great Red Spot in unprecedented detail. A swirling maelstrom larger than Earth, with internal structures like a hurricane's eyewall. It discovered Ios volcanoes, the first active volcanism beyond Earth. when navigation engineer Linda Morabito spotted a 300 km high plume on an image taken for optical navigation. "I thought it was a speck of dust on the film," Morabito recalled. "Then I realized it was a volcanic eruption on another world. I literally jumped out of my chair." Voyager 1 also discovered Jupiter's thin ring, a dusty, dark halo no one expected, and 2 new moons, Thebe and Métis. But it paid a price. Radiation degraded its camera system, forcing engineers to shut it down early to preserve the instrument for Saturn. Voyager 2, taking a slower, more treacherous path, survived Jupiter only to face Saturn in 1981. There, it discovered spokes in the rings, radial dark lines that defied explanation, later attributed to dust levitated by electrostatic forces, and measured Titan's thick, smoggy atmosphere. But the real heroism came later. Voyager 2 was the only probe to continue to Uranus, 1986, and Neptune, 1989, the only human artifact to ever visit these ice giants. By then, its power was failing. Its gyroscopes were wearing out. Its fuel for thrusters was critically low. Engineers pulled off miracles. They reprogrammed Voyager 2's computers remotely to compensate for degraded components, using Earth's most powerful radio dishes to send code that took 4 hours to reach the probe at light speed. The result: Uranus sideways, featureless blue disk revealed nothing at first, but hidden in the data were 10 new moons and the discovery that the planet radiated nearly 3 times more heat than it absorbed. Neptune's Great Dark Spot, an Earth-sized storm with 2,100 km/h winds, was captured in stunning detail before vanishing forever. By 2023, Voyager 2 was 20 billion kilometers away, still transmitting at 160 bits per second, slower than a 1980s modem, powered by a plutonium generator putting out less energy than a night light. These probes were designed for a 5-year mission, said project manager Suzanne Dodd. They've lasted 45. They're the most successful failure in NASA history. If the Voyagers were heroic flybys, Galileo, launched 1989, was humanity's first attempt to live in Jupiter's radiation hell. It was designed to orbit the giant for 8 years, studying it up close. Engineers knew it would be like building a house in a nuclear blast zone and expecting it to stand. The probe arrived at Jupiter in 1995 after a 6-year journey that included a clever slingshot around Earth and Venus. But the real nightmare began when it fired its main engine to enter orbit. To survive, Galileo was wrapped in a protective shell of tantalum, titanium, and aluminum, layers of armor that added 300 kilograms to its mass. Its most sensitive electronics were housed in a 1 centimeter thick titanium vault, a safe room designed to block radiation. It wasn't enough. Within months, radiation began degrading systems. The main antenna, a giant umbrella-like dish, failed to open properly, crippling data transmission. Engineers had to rely on a low-gain backup antenna that sent data at 10 bits per second, slower than a telegraph. It took weeks to download a single image. The radiation dosimeter recorded levels so high that if a human crew had been aboard, they would have received a lethal dose every 10 minutes. Jupiter's magnetosphere was essentially a cosmic microwave oven set to high. Galileo's camera, designed for 1,000 images, took 30,000 before radiation finally blinded it in 2002. The near-infrared mapping spectrometer died in 1999. The photopolarimeter radiometer failed in 2000. One by one, its instruments succumbed, sacrificing themselves to send back data that would have taken a century to collect from Earth. But the discoveries. Oh, the discoveries. Galileo found liquid water oceans beneath Europa's ice, confirmed by magnetic field measurements. It discovered that Ganymede has its own magnetic field, proving it has a liquid iron core. It watched Ios volcanoes erupt in real time, a planetary fireworks show. Most critically, in 1994, Galileo watched Shoemaker-Levy 9, a comet captured by Jupiter's gravity, slam into the planet at 60 kilometers per second. The impact scars were larger than Earth. Astronomers saw plumes hotter than the Sun, shock waves rippling through Jupiter's atmosphere, and dark scars that lasted for months. It was a preview of what happens when the solar system's garbage collector swallows something too big. By 2003, Galileo was dying. Its armor was failing. Its fuel was nearly gone. NASA made a decision. Rather than let it crash into a moon, potentially contaminating Europa's ocean with Earth microbes, they commanded it to plunge into Jupiter's atmosphere itself, a final, fiery sacrifice. On September 21, 2003, Galileo entered Jupiter at 50 kilometers per second. For 3 minutes, it transmitted data from a depth where pressure was 20 times Earth's and temperature melted its titanium shell. Then it vaporized. The final signal was a digital scream from inside a monster. Galileo's epitaph. It gave us Europa's ocean, Ganymede's magnetism, and proof that living in Jupiter's domain is a slow, cumulative death sentence. If Galileo was a battle of attrition, Cassini, launched 1997, was a masterclass in deliberate self-destruction. Its 13-year tour of Saturn, 2004 to 2017, became the most successful planetary mission in history, because it was designed to end in a controlled crash, gathering data until the final second. Cassini's instruments were generations beyond Galileo's. It carried a synthetic aperture radar to see through Titan's smog, revealing methane lakes and river valleys. It had a cosmic dust analyzer that captured and studied particles from Saturn's rings and Enceladus geysers. Its magnetometer mapped Saturn's complex magnetic field in 3D. But the mission's soul was the Huygens probe, a European-built lander that Cassini carried to Titan. On January 14, 2005, Huygens parachuted through Titan's orange smog, transmitting for 2.5 hours as it descended. It captured images of vast methane floodplains, rounded ice boulders on alien riverbeds, and a landscape that looked like Earth, but made of frozen water and liquid gas. It was like landing on Earth in an alternate universe, said imaging team leader Marty Tomasco. Huygens landed on a patch of icy pebbles and transmitted for 90 minutes before its batteries died. It remains the most distant human-made object to ever land on another world. The data it sent was stored on Cassini's hard drives and relayed to Earth over weeks, because direct transmission from Titan's surface was impossible at that distance. Cassini's own fate was sealed from day one. As its fuel ran low in 2017, NASA engineers plotted a series of 22 grand finale dives between Saturn and its innermost ring, a gap no spacecraft had ever entered, just 2,000 kilometers above the cloud tops. They knew radiation would kill it, but they also knew that by skimming the rings, Cassini could measure their mass, composition, and structure with unprecedented precision. The dives were suicide runs. Each orbit, Cassini passed through the ring plane where dust particles traveling at 20 kilometers per second could pierce its hull like bullets. The spacecraft performed flawlessly until the final orbit, when it was commanded to dive directly into Saturn's atmosphere on September 15, 2017. As it fell, Cassini's mass spectrometer sniffed Saturn's atmosphere, finding heavy molecules, complex organics, that suggested ring material was raining into the planet. For 30 seconds, it transmitted from a world where hydrogen was becoming metallic. Then it burned like a meteor, its last signal a burst of static. Cassini's legacy. 4,000 scientific papers, the discovery of Enceladus Ocean and its geysers, Titan's methane cycle, and proof that Saturn's rings are young, temporary, and ephemeral. Juno, launched in 2011 and arriving at Jupiter in 2016, is the most advanced probe ever sent to a giant planet. Its mission is specifically to survive long enough to map Jupiter's gravitational and magnetic fields, answering the question, what's inside? To do this, Juno flies in a highly elliptical polar orbit, diving to just 4,200 kilometers above the cloud tops every 53 days. This is the closest any probe has dared to go. At that altitude, Jupiter fills the sky completely. There is no horizon, only a wall of clouds that curves over the spacecraft like a ceiling. Juno's armor is 1 centimeter of titanium, the most radiation-hardened electronics ever built. Its solar panels are designed to function in a permanent twilight, receiving only 3% of Earth's sunlight. Its main engine is a backup. It uses Earth's gravity assist so precisely that it never needed a correction burn to enter orbit. But Juno is fighting a losing battle. Every orbit, it passes through Jupiter's most intense radiation belts, where electrons accelerated by the magnetic field strike its hull like machine gun fire. Its primary camera, JunoCam, was designed as a public outreach tool, not a science instrument, because NASA knew it would die first. And it is dying. Pixels are failing. Images show increasing static. By 2025, it will likely be blind. Yet the discoveries. Juno found ammonia plumes rising from deep in Jupiter's atmosphere, suggesting violent convection. It detected a fuzzy, diffuse core where a solid one was expected, proving that Jupiter's interior is far more complex than models predicted. It saw cyclones at the poles arranged in pentagonal and hexagonal patterns, resembling geometric storms on Saturn but more chaotic. Most stunningly, Juno's microwave radiometer looked beneath the clouds for the first time, mapping water content down to 100 atmospheres. It found that Jupiter's atmosphere is not well mixed. There are deep reservoirs of water, suggesting the planet formed in ways that current theories struggle to explain. Juno's mission is scheduled to end in 2025, when it will perform a controlled dive into Jupiter's atmosphere, just like Galileo. But unlike Galileo, which entered blindly, Juno will aim for a specific region near the Great Red Spot, attempting to measure the storm's depth before vaporizing. Why do we keep sending probes to die? Because every second of data from inside these monsters rewrites textbooks. Every death buys us a decade of understanding. While the giants got orbiters and landers, Pluto and the Kuiper Belt were ignored for decades. Then came New Horizons, 2006 launch, 2015 Pluto flyby, a probe so fast it crossed the solar system in 9 years, a journey that took Voyager's 12. New Horizons was built lighter and tougher than any previous probe. Its computer was a radiation-hardened MIPS RISC chip with 12 MB of RAM, less than a 1995 cell phone, but capable of surviving the radiation environment near Pluto, which, despite distance, was harsher than expected. The Pluto flyby lasted just 12 hours, but it was a masterpiece of precision. New Horizons had to hit a window just 150 kilometers wide at 14 kilometers per second. If it missed by even a second, it would photograph empty space. It hit perfectly. The images revealed ice mountains 5 kilometers high made of frozen water, floating on a nitrogen ice plain. They showed Sputnik Planitia, a heart-shaped glacier of nitrogen ice that slowly flows like a viscous liquid, erasing impact craters within millions of years. They detected blue skies made of tholins, organic compounds created when sunlight breaks down methane. But New Horizons wasn't done. In 2019, it flew by Arikov, a 35 km long contact binary in the Kuiper Belt, the most distant object ever visited by a spacecraft. The data from that 3,500 kilometers flyby is still being transmitted, at 1 kilobit per second. The full dataset won't arrive until 2026. New Horizons lesson. Even at the edge of the solar system, where giants are dim points of light, exploration is possible, if you're willing to wait decades for results. Let's be blunt. Sending a probe to a giant planet is a death sentence. The only difference is whether it dies instantly in the atmosphere, slowly from radiation, or by running out of power in the cold dark. The radiation math. Jupiter's radiation belts. 1 million rems/year at Europa's orbit. Lethal human dose. 500 rem. Time to kill an unshielded astronaut. 4.4 hours. Electronics. Standard commercial chips fail after 10,000 to 100,000 rem. Galileo's instruments received 250,000 rem before death. Shielding. Every centimeter of titanium reduces radiation by 50%. But at Jupiter, you need meters, not centimeters. The mass makes it impossible to launch. The thermal math. Entry into Jupiter's atmosphere. Speed: 48 kilometers per second. Atmospheric entry heating: 30,000 C. Apollo capsules experience 500 C on Earth re-entry. Probe survival time: Galileo 3 minutes. Juno planned 5 minutes. Any probe less than 10 minutes before melting. The fuel math. Getting to Saturn requires 3 to 5 years with gravity assists, or 7 to 10 years direct. Once there, you need fuel to break into orbit. Cassini carried 3,000 kilograms of hydrazine, so much it nearly doubled launch mass. Even then, after 13 years, it had only 1 kilogram left for the final dive. Conclusion: every giant planet mission is a kamikaze mission. The only question is how long the suicide note, data transmission, lasts. The Magnetic Titans, Invisible Shields and Particle Guns, Chapter 9.1. Jupiter's magnetosphere. The largest object in the solar system. If you could see magnetism, Jupiter would dominate the night sky. Its magnetosphere, the region of space where its magnetic field dominates over the solar wind, is 7 million kilometers wide, 150 times Jupiter's own radius. It stretches to Saturn's orbit, making it the largest continuous structure in the solar system after the Sun itself. For comparison, Earth's magnetosphere extends about 10 Earth radii. Jupiter's is 15 times larger. It captures solar wind particles and accelerates them to relativistic speeds, creating radiation belts that would kill a human in seconds. But the real magic is how it generates this field. The dynamo in depth. Jupiter's metallic hydrogen ocean, 40,000 kilometers deep, rotates at different speeds at different latitudes. Differential rotation shears the conductive fluid, stretching and twisting magnetic field lines like taffy. This dynamo effect generates currents of 10 billion amps flowing through the planet's interior. The result: a magnetic field 20,000 times stronger than Earth's, with a magnetic moment 18,000 times greater. If you place the compass on Io's surface, which orbits within this field, it would point not to Jupiter, but to the magnetic equator, spinning wildly as Io moves through field lines. Juno's discovery. The field is not symmetric. It's lumpy, with intense blue spots near the poles where field lines converge. This suggests the dynamo is chaotic, with turbulent plumes of metallic hydrogen creating localized magnetic storms. Implication: Jupiter's magnetic field is not stable. It pulses, shifts, and may even flip poles over timescales of thousands of years, something Earth does every 300,000 years. If you could live long enough, you'd see Jupiter's auroras wander across its poles like wandering stars. Saturn's magnetic field is a paradox. Weaker than Jupiter's, 600 times Earth's, but perfectly aligned with its rotation axis, unlike any other planet. Earth's magnetic poles are tilted 11 degrees. Jupiter's are 10 degrees. Saturn's are 0 degrees, a cosmic coincidence so precise it baffled scientists for decades. Cassini's magnetometer revealed why. The field is generated not at the core, but in a shallow layer of metallic hydrogen just 20,000 kilometers below the clouds. This layer is turbulent, but Saturn's rapid rotation, 10.7-hour day, smooths everything into perfect alignment. Yet Saturn's field has odd anomalies, kinks and bends where the field lines tangle. These are caused by its rings. Yes, the rings affect the magnetic field. Ice particles become charged and drag field lines with them, creating magnetic footprints that leak radiation down into the atmosphere. Cassini saw this. During the grand finale dives, it detected beams of energetic particles flowing from the rings into Saturn's upper atmosphere, a slow, invisible erosion that will consume the rings over 100 million years. Saturn's magnetic secret. It's dying. As its interior cools, the metallic hydrogen layer contracts, and the dynamo weakens. In a billion years, Saturn may lose its magnetic field entirely, becoming a cold, dead giant like Uranus. Uranus' magnetic field is the weirdest in the solar system. It's tilted 59 degrees from its rotation axis, and its center is offset by 1/3 of the planet's radius. The result. The field looks like a drunkard trying to stand straight, wobbling wildly as Uranus rotates. The cause? Uranus ice interior, a slushy mixture of water, methane, and ammonia, conducts electricity poorly compared to metallic hydrogen. The dynamo is weak and shallow, generated in a thin layer near the boundary between ice and rock. Voyager 2's discovery. The field is asymmetric. One hemisphere has a magnetic strength of 0.1 Gauss, similar to Earth's. The other has 1.1 Gauss, stronger than Saturn's. This means that at certain times, Uranus' southern hemisphere is bathed in intense radiation, while the north is relatively calm. Implication for life? If any future probe tries to orbit Uranus, it must choose its altitude carefully. Flying over the strong hemisphere means facing radiation doses 10 times higher than over the weak one. It's a magnetic minefield. Neptune's field is stronger than Uranus, 0.15 Tesla at the surface, but just as lopsided, tilted 47 degrees and offset. Yet Neptune generates more internal heat, which should power a stronger dynamo. The paradox. Neptune's dynamo should be in its ice layer, like Uranus, but its heat source is different. Helium rain, droplets of liquid helium falling through the metallic hydrogen, creates extra convection, boosting the dynamo. Result. Neptune has the strongest winds in the solar system, 2,100 kilometers per hour, driven by both internal heat and magnetic forces. The field drags charged particles from the solar wind and its own ionosphere, accelerating them into massive auroras that dwarf Earth's. New Horizons distant observation, 2020, revealed that Neptune's auroras pulse every 16 hours, its rotation period, suggesting the field is locked to the interior in ways we don't yet understand. The takeaway. Each giant's magnetic field is a unique fingerprint of its interior. Jupiter's is brute force. Saturn's is precision. Uranus is chaos. Neptune's is defiance. Together, they prove that there's no single way to be a giant, only different paths to cosmic monstrosity. The moon worlds, 4 planets trapped in orbit. Io isn't a moon. It's a failed planet that got too close to its star, Jupiter, and was turned into a weapon. Its surface is sulfur-coated lava that erupts not from heat, but from tidal torture. The numbers. 400 active volcanoes at any moment. Eruption plumes reach 500 kilometers. Space starts at 100 kilometers on Earth. Lava temperatures. 700 C, hotter than Earth's basalt. Surface renewal rate. 1 centimeter per year. In 10 million years, Io's entire surface will be replaced. Geologically, Io is younger than human civilization. The cause. Io sits in a gravitational vice. Jupiter pulls it inward. Europa and Ganymede pull it sideways in a 4:2:1 orbital resonance. The result. Io's crust flexes by 100 meters every 42 hours. Rock rubs against rock, generating friction heat that melts the interior. The plume of Pilinpatera, 1997, was so powerful it was seen from Earth telescopes. The heat output was 1,013 watts, equivalent to 10,000 nuclear power plants. The paradox. Io has no impact craters. Any asteroid that hits is instantly buried in fresh lava. Io is the only world in the solar system whose surface is younger than Mount Everest. Future fate. As Europa slowly drifts outward due to tidal interactions, the resonance will break. Io's volcanoes will die. It will become a dead, cratered rock like Callisto. But that won't happen for 100 million years. Until then, Io is the solar system's most reliable horror show. Europa is the most likely place to find alien life in the solar system. Here is why. The ocean, confirmed. Depth: 60 to 150 kilometers, Earth's oceans. Average 3.7 kilometers. Volume: 2-3x all Earth's oceans combined. Salinity: similar to Earth's Dead Sea, highly salty, which prevents freezing. Temperature: -4C to +10C at the seafloor, heated by tidal flexing, like Io, but gentler. The crust, cracked, Europa's ice shell is 15 to 25 kilometers thick, but it's not solid. It's a scratched eggshell. Linear cracks. Thousands globally, some 3,000 kilometers long, Earth's longest fault. 1,500 kilometers. Chaos terrain. Regions where ice has broken into floating rafts, refrozen, a sign of subsurface activity. Plumes. Hubble spotted water vapor jets 200 kilometers high in 2012 and 2016. Juno detected them in 2022. Europa is venting its ocean into space. The seafloor active, Europa likely has hydrothermal vents, underwater volcanoes. How do we know? Magnetic field data shows induced currents in the ocean, requiring salty, conductive water. Galileo's gravity data suggests a warm, low-density layer at the seafloor. Comparison to Earth. Our deep ocean vents host entire ecosystems: tube worms, crabs, bacteria, powered by chemical energy, not sunlight. The dolphin problem. If Europa's vents are like Earth's, then anaerobic microbes should exist. If microbes exist, they could evolve into multicellular life. If multicellular life exists, intelligence is possible, on a timescale of billions of years. Europa Clipper, 2024 launch, will fly by 45 times, using ice-penetrating radar to map the ocean. NASA's goal: find the vents. Because vents mean life. The ethical nightmare. If we find life, do we land? Contamination risk is 10 to 20% with current sterilization. One Earth bacterium in Europa's ocean could trigger an ecological collapse, or a hybrid biosphere. Conclusion. Europa is a moral test. It's the place where science meets philosophy. And it's waiting. Ganymede is bigger than Mercury and has its own magnetic field, yet it's a moon. If placed in orbit around the Sun, astronomers would call it a planet without hesitation. The magnetic dynamo unique. Ganymede's field is 0.001 Gauss, weak compared to Earth's 0.5 Gauss, but it's generated internally, not induced. This requires a liquid iron core radius 500 kilometers. Tidal heating from Jupiter and Europa. Radioactive decay, potassium-40 in the rocky mantle. Juno's 2021 flyby confirmed the field is dipolar, like Earth's, meaning Ganymede is a true geodynamo, a miniature Earth inside a gas giant's domain. The ocean sandwich unique. Unlike Europa's single ocean, Ganymede has multiple ocean layers, separated by exotic ice phases. 1. Ice surface, normal water ice. 2. Ice 2 and 3, 50 kilometers down, dense, hot ice formed at 2,000 atmospheres. 3. First liquid ocean, 100 to 150 kilometers, salty, possibly 3x salter than Europa's. 4. Ice VN6, 200 kilometers down, exotic, conductive ice that may short-circuit the magnetic dynamo. 5. Second liquid ocean, 300 to 400 kilometers, deeper, warmer, pressurized to 10,000 atm. Why this matters? The interaction between these layers could create chemical gradients, different pH, salinity, temperature, perfect for prebiotic chemistry. Ganymede isn't just an ocean world, it's a lab with multiple experiments running. The atmosphere, negligible but critical. Ganymede has a tenuous oxygen atmosphere, created when radiation splits water ice. It's 1 trillion times thinner than Earth's, but enough for auroras to form when particles from Jupiter's magnetosphere strike it. Juno observation. The auroras pulse every 7 hours, Ganymede's orbital period around Jupiter. This proves the magnetic field interacts with the giants in real time. Future mission. ACE's JUICE, Jupiter Icy Moons Explorer, launch 2023, will orbit Ganymede in 2034, the first moon of another planet to become a primary spacecraft target. It will map the magnetic field, radar sound the ice, and search for magnetic anomalies that could indicate hydrothermal vents. Bottom line. Ganymede is the most Earth-like world in terms of internal dynamics. If it has life, it might be more advanced than Europa's microbes, multicellular, even complex. Callisto is the anti-Europa. If Europa is a promise, Callisto is a warning. The surface ancient. 4 billion years old, virtually unchanged. Impact saturation. Every square meter has been hit multiple times. No tectonics. No tidal heating, no internal renewal. Ganymede's albedo. 0.43, reflective. Callisto's. 0.12, as dark as coal, stained by eons of meteoritic dust. The slow death. Callisto never formed in resonance. It's too far, 1.9 million kilometers from Jupiter, for tides to matter. Its interior is cold, dead rock and ice. But it has an ocean, maybe. Magnetic data from Galileo shows a weak-induced field, suggesting a salty ocean at 150 to 200 kilometers depth. But it's not tidal. The heat source is radioactive decay of K40, U-238, Th-232 in the rocky core. Temperature. -20°C, barely above freezing. Salinity. Extremely high, like the Dead Sea, but colder. Energy. Negligible, no vents, no convection. If life exists here, it would be the slowest life in the universe. Bacteria that reproduce once per 1,000 years. Metabolism so low it's barely detectable. A biosphere in suspended animation. The time capsule. Callisto is the control group for the experiment of life. It has water, organics, from meteorites, and some heat, but not enough to start the engine. It's been 4 billion years of near nothing. Conclusion. Callisto tells us that life needs energy, not just ingredients. Water and carbon are common, tidal heating or geothermal vents are rare and essential. Future use. NASA has studied Callisto as a base for human exploration of the Jovian system. Its distance means radiation is 100x lower than at Europa. Its stable surface means landing is safe. It could be the gateway to the more interesting, more dangerous moons. Titan and Enceladus. The two faces of habitability. Titan is the only moon with a substantial atmosphere, 1.5x denser than Earth's, and the only surface in the solar system besides Earth with stable liquid. But it's methane, not water. The hydrological cycle, methane addition. Evaporation. Methane lakes at -179°C release vapor. Condensation. Forms methane nitrogen clouds. Precipitation. Methane rain falls, carving channels, filling rivers. Runoff. Rivers flow into lakes, which slowly evaporate. Cassini's radar mapped hundreds of lakes near the poles. The largest, Kraken Mare, is 400,000 kilometers, larger than the Caspian Sea. It's 300 meters deep and has waves up to 1 centimeter high, detected by radar. Tides are influenced by Saturn's gravity. The surface, organic sand dunes. Titan's equator is not liquid. It's organic sand dunes made of tholins, sticky, tar-like particles that settle from the smog. They form longitudinal dunes 100 meters high, shaped by winds that blow east to west, opposite Earth's trade winds. Huygens probe landed on a pebble-strewn plain. The pebbles were water ice, rounded by methane flow. The soil was organic mud, brittle at -179°C. The prebiotic chemistry. Titan's atmosphere is a chemical factory. Methane, CH, ethane, CH, propane, acetylene. Nitrogen, N, cyanides, HCN, nitriles. UV radiation complex polymers, tholins, that rain down. NASA's Dragonfly mission, 2027 launch, will send a nuclear-powered drone to fly in Titan's thick atmosphere. It will land, sample, and fly to dozens of sites, searching for prebiotic molecules that could form life's building blocks. The what if? Titan is a frozen early Earth. If it warmed by 200 C, its methane cycle would become a water cycle, and tholins could become amino acids. Titan is paused at the moment before life begins. While Titan is Earth's frozen twin, Enceladus, Saturn's tiny moon, 500 kilometers wide, is the most accessible ocean. The plume, confirmed. 100 plus active geysers at the South Pole. Water vapor plus organic molecules, detected by Cassini. Escape velocity. 240 meters per second. The plumes reach 2 kilometers per second, 8x escape speed. They form a tiger stripe pattern of fractures. Cassini flew through the plume in 2015, just 49 kilometers above the surface. Its mass spectrometer detected hydrogen gas, H, methane, ammonia, and complex organics. The hydrogen is key. It means hydrothermal vents at the seafloor are producing chemical energy, exactly like Earth's vent ecosystems. The ocean, thin but global. Thickness: 30 to 40 kilometers under 20 to 30 kilometers of ice. Volume: 10% of Earth's oceans. Age: 100 million years, based on crater counts. It formed recently, geologically, when Saturn's gravity flexing increased. Why Enceladus is one for life. 1. Accessibility. Plumes deliver ocean samples for free. No drilling needed. 2. Energy. Hydrothermal vents proven by H detection. 3. Organics. Cassini found amino acid precursors. 4. Youth. The ocean is active now, not a frozen relic. NASA's proposed Enceladus Orbalander would orbit, sample plumes, then land near a fracture. It could detect microbial biosignatures directly. The urgency. Enceladus vents could die in 10 million years if Saturn's tidal flexing changes. We might be living in the only window to see it alive. Future missions: the next 30 years Europa Clipper, NASA, 2024 launch. Goal: 45 flybys, closest approach. 25 kilometers. Radar. Reason can penetrate ice to 30 kilometers depth, map ocean. UV spectrometer. Detect plumes composition. Magnetometer. Confirm ocean depth and salinity. Life detection. Not directly, but will find biosignatures, organic molecules, salts, pH gradients. Landing mission, 2030s. NASA plans a follow-up lander with a cryobot, melting probe, to reach the ocean. The challenge: sterilization. No Earth microbes can contaminate Europa. The lander will be baked at 500 C for 50 hours and irradiated with gamma rays. More sterilization than a surgical suite. Cost: $4.25 billion. The most expensive life detection mission ever. Dragonfly is NASA's most creative mission. A quadcopter flying in Titan's thick atmosphere. Launch 2027. Arrival 2034. Power radioisotope thermoelectric generator, RTG, no solar needed in Titan smog. Payload mass spectrometer, cameras, seismometer. Flight plan: land in Shangri-La dune fields, then fly 8 kilometers hops to dozens of sites over 3 years. It will study Tholin chemistry at different altitudes, prebiotic molecules and surface organics. Seasonal methane cycle. Titan's year equals 29 Earth years. Dragonfly will see 1 full season. The Miller-Urey test. Titan's atmosphere is a natural prebiotic lab. Dragonfly will find complex organics that could become life if Titan warmed. NASA's Decadal Survey, 2023, flagged an ice giant orbiter as the one priority for the 2030s. The Neptune Odyssey concept. Launch 2033, requires Jupiter gravity assist. Arrival 2049. Orbiter. Nuclear-powered, 10-year mission. Probe. Atmospheric entry probe to measure composition, winds, temperature. Science goals. Measure the diamond rain via atmospheric entry. Map magnetic field anomalies, Uranus lopsided field, Neptune's dynamo. Study ring dynamics. Why are ice giant rings so dark? Ocean worlds. Triton, Neptune's moon, has active geysers of nitrogen, maybe a subsurface ocean. Cost: 3 to 4 billion. The long travel time, 16 years, is the biggest barrier. Politicians want results within election cycles, not generations. Fusion propulsion, Project Icarus. 20-year flight to Neptune versus 40-year chemical. Magnetic confinement of deuterium helium-3 plasma. Status: lab experiments only 30 years from flight. Laser sails breakthrough star shot. Giant laser array on Earth pushes a gram-scale probe to 20% light speed. Reach Neptune in 1 day. Problem: no way to slow down. It's a flyby at relativistic speed, no data return. Cry about submarines, NASA stake. Melt through ice using a hot nuclear core. Deploy submarine in the ocean. Tested in Antarctica, Lake Vostok. Worked, but sterilization remains impossible with current tech. Can't guarantee no Earth contamination. Conclusion: for the next 30 years, Clipper, Dragonfly, and an ice giant orbiter are humanity's only realistic shots at giant planets. We'll get spectacular data, but no humans will visit in our lifetime. The giants are simply too lethal, too far, too expensive. The philosophy: what giants teach us about life. The giants force us to confront the Fermi paradox. If life is common, where is everybody? The rare Earth hypothesis argues that complex life requires 1. A stable star, G-type like the Sun. 2. A gas giant guardian, Jupiter, to deflect asteroids. 3. A large moon, Earth's moon, for axial stability. 4. Tectonic activity, plate tectonics recycles carbon. 5. A magnetic field, shields from radiation and solar wind. Jupiter's role: 80% of potentially hazardous asteroids are ejected by Jupiter's gravity. Without it, Earth would be hit 1,000x more often. Life might never evolve past bacteria. But Jupiter's migration nearly sterilized the inner system. The Grand Tack was a coincidence. If Saturn hadn't been at the right mass and time, Jupiter would have kept moving inward, destroying everything. Conclusion: gas giants are a double-edged sword. They protect life, but only if they stop at the right distance. The odds of this are less than 10% in simulations. Most solar systems either have no giant or a migrating one that kills inner worlds. We live in a cosmic window. Jupiter's current orbit. Stable for 100 million years. Saturn's rings. Visible for 200 million years. Europa's ocean. Warm enough for maybe 1 billion years. Enceladus plumes. Active for maybe 10 million years. We are observing the giants at a special time. If humans had evolved 200 million years later, Saturn would be ringless. If 500 million years earlier, Jupiter might have been migrating. The anthropic shadow. We must exist in a time when conditions are right, or we wouldn't exist. The giant's current state is not typical, it's necessary for us. Europa's ocean might have life. Enceladus definitely does. Titan might have prebiotic chemistry. If we find life, 3 possibilities. 1. DNA-based. We're related, life spread by meteorites, panspermia. 2. RNA-based. Independent origin, proves life is common. 3. Something else. A third genesis, life is inevitable. Option 3 is the most profound. It means water plus energy plus organics equals life everywhere. The universe is teeming. The risk. Contamination. We could kill what we seek. Current sterilization kills 99.9% of microbes, but 0.1% survive. That's still millions of bacteria on a probe. The ethical dilemma. Do we have the right to risk another biosphere for our curiosity? NASA's answer. Yes, with extreme caution. Sterilized to spore level 300, no more than 300 surviving microbes. That's stricter than hospital sterilization. But it's still a risk. And if life is found, who gets to make contact? Do we send a submarine? Who owns the data? Who speaks for Earth? Jupiter is 318x Earth's mass but has no surface. Saturn's rings are 100 million years old, younger than dinosaurs. Uranus is on its side from a collision. Neptune has 2,100 kilometers per hour winds from internal heat we don't understand. The lesson? Nature doesn't care about our categories. A planet can be a moon. A moon can be a planet. A ring can be temporary. A storm can last centuries. The giants teach humility. We are tiny, fragile, and temporary. Our existence is a statistical miracle, a narrow window in a chaotic solar system that could have easily erased us. The call. Explore while we can. The window won't stay open forever. Like and subscribe to our channel so you don't miss our new videos which, as always, expand the fringe of the known.